Good. Okay, go for it. So you guys, unit 7 batteries. Basically, I'll summarize the unit. If the battery's bad, replace it. All right, we're done. No, just kidding. There's actually quite a bit to know. So why do we have a battery? You guys know the vehicle, the car, relies on electrical power to assist in the management and control the engine, emission systems, and also other aspects of the vehicle. So let's say, for example, brakes, suspension, the navigation, entertainment, information, your gauges, like a big percentage of your car is electrical. So we need a whole electrical system for all this type of stuff, and the battery plays a key role in that. So when you think about, one thing we were just talking about was, if you have issues with all these systems, they could all actually come back to an issue with the battery. Like we heard about this service stop start system that ended up just being a battery that was discharged. Okay, so if you also can consider this, let's say we'll pick one. We'll look in suspension, but we'll actually change that slightly to steering. A new car would have electric power steering. An old car would have like a hydraulic power steering with a belt and fluid. So the trend has been going away from mechanical things, going to electrical things. So there's even more and more demand on that battery. And even further too, like the whole charging system as a whole, which we're going to be covering in the next 2 units. So this is batteries, then we do starting, then we do charging, and they all kind of tie together. Okay, so as we continue, what is a battery? So let's just say electricity cannot be stored easily in its electrical form for later use. So when you want to get in the car and you want it to go vroom, what do you have to do? All right, so when you say turn it on or start it, think of like what that actually means. We need to take electricity and we need to send that electricity to the starter, because the engine, once the engine's running, you're kind of self-sufficient, but you got to turn the engine over to get it started. So let's say we went back in time. Remember when we had horse and carriages, and we had like the horseless carriage, and it was kind of like the first vehicle. Do you know what you had to do to start those? Anybody actually know? Yeah, the hand crank. People would end up with broken arms. They'd hit themselves in the face. Yeah, you'd have to go to the front and you'd put this like wrench, this little crank into the crankshaft, and you'd actually, it was really tough to do. Well, that's what the starter does for us. And the starter needs electricity. So we store the electricity in the battery, right? It's kind of weird, but mainly that's the purpose of the battery. We can store electricity in there, although it's kind of in a weird way. And then when we want it, we can take the electricity back out. Okay, so like if we zoomed out for a second, we send electricity in the battery stores it until we need it later, and then the battery gives it. So it's almost like a little piggy bank for electricity if you think about it like that. Now, because we can't really store electricity itself very well, it must be stored in another form of energy. Interesting. And then it needs to be reconverted into electricity when needed. So now let me explain that a bit. It's stored actually in the form of chemical energy. So it's kind of crazy, but inside your battery, it's mostly like it's a science experiment in there. It's chemistry. As we charge the battery, the chemistry changes. And then when we want to get energy out of the battery, we let the chemistry change back to how it was, and it puts off electricity. I know it sounds kind of crazy, but that's actually what's happening in there. So the chemical reactions change the composition of the chemicals, which then are stored until the electrical energy is needed. Okay, so we'll go into a bit more detail on this, but kind of what I'm saying is like this battery right here is actually fairly charged, whereas this battery right here, yes, it's smaller, but this battery right here is discharged. The only difference between these two is really simple. They don't, in actuality, they don't contain electricity. This has one chemistry and this has a different chemistry. This one's kind of heavy, so let me pick a lighter one. In fact, let me pick one that's a cutaway. This one has no energy in it. You know how I know? It's cut away and drained. All right, so this is what's weird. If this one's totally discharged, it's not that it ever had electricity in it, but we put electricity in there, which changed the chemistry in these plates and in this battery acid. And then if we charge it up, it becomes like, let's say this one that's now charged. Then if we want this to discharge, we can convert this chemistry, this chemical energy, into electricity and then have the electricity do work for us. It's really crazy what's happened in this battery.
What is that battery used?
This one is actually, so this was probably out of a motorcycle, and it's cut away so that we can see the different plates. Like some we'll get into a little bit more so you can kind of know what's happening in there. So let's look at the system overall. Here's your battery. We would say that's the main source of electrical energy in the vehicle, but I'd like to tweak this a little without going too much into charging systems. This battery stores your electricity, but you know what it really does? We put electricity into it and it changes it into chemistry. Then when we want the electricity back out, the chemistry changes it back into electricity. Make sense? So we put the energy in the battery as the vehicle's running, then we shut the vehicle off. Then when we want to restart it, that's when we really need this. So the battery's most difficult time is getting the car started. Then if this sends electricity to the engine through the starter and the starter motor gets it cranked up, once the engine's running, the battery's job is a lot easier because the engine will be running, and when the engine's running, it turns the belt. And does anybody know where the power comes from when the engine's running? Exactly. Once the engine's running, mainly the alternator is powering a lot of stuff, but the alternator is not real smooth. You know, the alternator is gonna produce electricity, but it might not be like really, really steady. You know, if you rev it up, the alternator voltage will actually go up. And if you let it sit at idle, it'll go down. So while it's running, the battery functions more as like a buffer. So a buffer meaning it'll stabilize the electricity. The alternator will put out what it needs to put out, which is mostly charging the battery. But if you come to an idle and the alternator's a little low, no problem. The battery's more than charged enough to step in and fill in the low spots. And then if you're revved up and the alternator's putting out a lot, it's okay. The battery can absorb the excess. Make sense? So in the go out to the car and get ready to start it, the battery supplies all the power. And that's very hard on the battery. Then once it's running, the battery mostly just acts as a buffer. That kind of like a good overall view of the system. And that's what it means by it provides energy to operate the lights and accessories and to start the engine. And that's true, but in a way, the alternator is really kind of powering that stuff through the battery, but it does serve as a voltage stabilizer. So that's what I mean by a buffer. It's going to stabilize it. It's going to make it so it's never too low. It's never too high. Cool. Now, when we get into what the battery is, so like we're saying, you go out to the car and you need to start it. Remember, that's the hardest job of the battery. When we need the electricity, such as starting, the chemicals are going to react with each other, transforming the chemical energy back into electrical energy, right? So if you didn't want to know that, like if you're just a DIY person and you're like, that battery stores electricity, that's okay. Because when the battery's dead, you know that maybe you need a new battery or you need to charge it with electricity, right? But as a technician, you're going to run into these problems where you actually need to consider it's really storing chemistry. And then let's say like the traditional battery is called the lead acid. So this is a lead acid battery right here. I know because it's clear cutaway. It actually has a lower level and a higher level. And you could see these plates, some of which are lead. That's going to be immersed in like you ever shook a battery and noticed it makes a sound like there's some liquid in there? Right? That's like a flooded lead acid, traditional, normal, old school, if you will, battery. That's kind of what we're talking about here. But they come in many different shapes, sizes, and whatever. And lead acid's not the only option. That's just the one we're going to start with. But if you look at it, we've got negative plate, insulator, positive plate. And this is all immersed in this solution, this electrolyte. It's like battery acid, we'll call it. Sometimes we'll call it electrolyte. This is the storage of that electricity, right? We'll actually put electricity in and it'll change the pH of this. It'll change the acidity, and that'll store it. So as we charge it, it changes the acidity, and as we discharge it, it changes the acidity, right? So it's kind of crazy, but this is just a big chemistry experiment, really. Now keep in mind these plates, okay, because we're going to come back to those. And then the demand on a battery, this is the main demand. They're designed to provide high current draws for short periods of time. What's that mean to you? Remember, the battery's hardest job is to, right, so like for a few seconds, it's going to have to send a whole bunch of electricity, a whole lot of amps. Remember, amps is like the current flow. So a high amperage, high current to run the starter, so that way the starter can right? Turn the engine, build compression, fire the spark plug, fire the fuel injector, and then all of a sudden, boom, the engine's running on its own, and the battery's like, oh, that was really hard work for 6 seconds, or maybe 2 seconds if it's a newer car. Now, if you get a car that's hard to start because it's got some engine performance issue, low compression or fuel or something, you see how that's going to be harder on the battery? The battery's going to be like, all right, here we go. I'm ready to do my quick 5-second sprint, and then it's and the battery's like, ugh. Those cars tend to damage the batteries a little quicker when the car is hard to start. Makes sense? Okay, and then that's the traditional automotive battery. Lead acid's really good for that. These types of batteries, they're great for that. Like, I'll give you like 30 seconds of really high amps. Now, let's just say your concern was a little bit different. Let's say you weren't dealing with a car. Let's say you wanted an off-grid cabin in Idlewild, and you wanted the solar to charge that battery during the peak sunny times, and then all night long you want that battery to be able to power your lights and heat your water and that type of thing. That would be like a longer drawn out discharge, right? That'd be better for like a deep cycle. A deep cycle battery would be a better fit for that. Deep cycle battery is going to supply a smaller continuous loads over longer periods of time. So there's different types of batteries depending on what the application is. But generally for automotive, our main concern is getting the engine started. Make sense? And then I even give you like a little sneak peek. Lithium batteries have become really popular. So I say right here, various lithium battery chemistries. You're like, what? So lithium, what? Ion, iron phosphate, manganese, I don't know. They have all sorts of lithium mixed with other stuff. They're gaining popularity, and we'll get into those a little bit. In automotive, we're not using a ton of these from the factory, but a little bit. We're starting to see some more. And then aftermarket, we're using a lot of these. And then if we were to get into something where we want a deep cycle battery, like for like a house backup, yeah, lithium is going to come in really strong. Lithiums are amazing batteries. They're not necessarily as simple and cheap as this though. So if all we're really trying to do is get the car started, I don't know if it's worth spending 3 or 4 times the price on a lithium, X, Y, and Z type of lithium. So let's talk about different batteries. These are your general automotive batteries. So we're not going to really use these for the whole home backup or the Tesla batteries or EV batteries. This is more like your normal car. Lead acid is the common. And then this is not necessarily lead acid or non-lead acid, but a low maintenance or a no maintenance. We're gonna group those together. Old school, if this was your lead acid battery, you'd actually periodically pop this cap off right here, and you'd actually look in there to see if any of those cells were a little bit low, and they should really all be the same. But let's just say your electrolyte level went down. You could actually add typically distilled water back in there, because the theory is the electrolyte, the battery acid part didn't really evaporate, but the water could evaporate out of it. So we would add the water back in. So if you were to look at a battery like this one, you don't even really see any of the markings. But if I showed you this one, you guys see how this one's kind of clear and it has a low level and a high level. If you were to look at this and be like, oh, it's below the low, you might actually have to pop these little caps off right here and actually put some
Distilled water, right?
distilled, yeah. And go ahead.
When I used to work with forklifts a lot of times.
Oh yeah, they'd have them.
Do that with batteries.
Yeah, and this is nice because you can actually do some of the basic maintenance, but the thing is, a lot of times people weren't really doing it, and my understanding, the main problem is when you have this cap right here, it's hard to get it to be 100% sealed, and so if this isn't sealed, you could see how the water would be more likely to evaporate. So rather than that, they go to the low maintenance or the no maintenance, where basically this is all sealed. So if we were to look at this O'Reilly's battery, this Super Start, and this is the battery test, and I'm actually going to come back to it, but if I peel this off, you're going to notice there is no little caps and covers and stuff. It's just like, this is basically like you can't do anything. Some people would call this a sealed battery, but the truth is it can never be totally sealed, because as this battery heats up, you know, it's going to expand, and they have to be able to vent off some of those gases. So if you didn't vent it, you know, this thing could kind of like bulge out. When you charged it, it gets hot. It could kind of like swell up. And then when you discharge it, you know, it would kind of collapse on itself. So we'll typically vent these, but this is your traditional old school. You can add water to it. You know, you could do some maintenance. Not real common anymore. Although on some things like forklifts make sense, or bigger equipment that's really maintenance in mind type of design, they'll keep these types of batteries, because if you have a maintenance department, you could roll it in and they could check the electrolyte level, you know, and they could tweak it. But to be really honest, in automotive, we're going to less and less and less and less and less maintenance. So if you just go back like 20, 30 years, probably really 20, we were doing bigger tune-ups, spark plugs, and if you go 30 years, we're doing cap rotor wires. We're doing valve adjustments. We're doing like timing belts. We're doing all this intense maintenance. But the thing is, most people, they don't want to pay for that. So if, let's say you're a manufacturer, right, and you come up with your own car company. Let's say we come up with El Cheapo Motors, okay? El Cheapo Motors, you buy the car and you basically do no maintenance. You don't have to pay for an oil change. You don't have to pay for tire rotation. You don't have to pay for anything. That car would sell, because people don't really want to keep putting money into it, right? So if you are a customer driving your average car, you don't want to come in and be like, oh yeah, can you guys inspect my battery and pop the cap off and adjust the electrolyte level and stuff? Like, yeah, but we're going to charge for it. They don't want to pay, right? So we've really gone away from this and gone more to these. And that way, when the car comes into the shop, like your typical modern vehicle, it looks like this, and you're like, okay, the battery looks, I don't know, I can't see, I don't know, I really don't care. So the way that we do the battery maintenance has changed. We'll come back to that. Generally, we don't do battery maintenance. We just do like periodic inspection, but it's on battery performance, not fluid level, not electrolyte level. And then let's take a look at vented and sealed. Sealed is not common, but they do actually have sealed batteries, like let's say this one. This battery is totally sealed. This battery is not going to be lead acid though. So lead acid could be low maintenance, no maintenance. Lead acid is going to be vented, but if you want to get into a sealed battery, it's not likely to be lead acid, because remember, that's the one where it's expanding and contracting. This is more likely when it's a sealed battery, because it needs to be in a motorcycle. It's going to be upside down and right side up and leaned over and flipped over and all sorts of stuff. They'd go sealed, but it's more likely to be this type, an AGM. So right there, AGM, everybody clear? No. Absorbed glass mat. So this battery, do you hear any shaking, any liquid splashing? No, because there's no liquid per se in here. It can be gel, or it can be like glass mats that have the electrolyte absorbed into the material, and there's no movement in there. So those don't really need to be vented, but some types of AGM are vented. They can kind of vary, but if it's in a car, we don't expect the car to be upside down. So a lot of times we'll keep them vented. But like a picture I'll show you later will show we actually will a lot of times vent those outside. Okay, so like this one, Couldn't remember if it was the next one or not. This is an AGM battery. They'll consider it sealed, maintenance-free, but it's inside. You notice how it's inside? And then right here, you can just barely tell, but there's a little tube. See this tube right here? This tube comes up, and a lot of times will go to the battery. So they may be totally sealed, or they may be like kind of sealed, but they know there's a chance it could have some off-gassing, and that gas is really problematic. So they'll put a little vent right here. So let's say you being the upcoming technicians, you go to replace this battery. It's very important you get the same type of battery, right? Because we're going to undo it. We're going to undo the terminals. We're going to put the new one in. We're going to clamp it down, right? Standard stuff. Put the terminals on. But then there has to be a point where we can connect this vent, because otherwise, if it's venting not through the little tube, where's it venting? Yeah, exactly. And that's where we can have a problem, right? So that's some of the reason we want you guys to understand there's these different types. It's not, sometimes the book likes to get really in detail about the exact science and the chemistry stuff, and sometimes I skim over that. But you need to understand, if it came with a vent and you put a new one in there, that vent, there better be a vent spot for that hose on the new one. Cool. So this was the typical lead acid. So sometimes we'll call it like a wet cell. Sometimes we'll call it a flooded cell. So if you go on a battery tester and the battery tester asks what type it is, and it gives you an option of flooded, wet, or lead acid, those are all the same. That's all the same stuff. That's like the ones with the liquid in them. So if you were to just look at a battery and you could see the little caps, or you could see it's clear, like those are for sure flooded. If you were to look at a battery that's, let's say like this, I wouldn't know for sure. So I would actually have to read it and be like, oh, okay, this one says AGM, right? So by default, typically it's going to be a flooded or a lead acid battery. That's very important when you go to charge and test it. They charge slightly different. Make sense? And then the reason it's called a flooded is because the lead plates are immersed in the water/acid electrolyte solution. Makes sense? So that's where the liquid's in there. And they're really good. They can supply very high discharge currents. So like let's say you're in Alaska. That would be kind of cool, but also that battery's got a really hard life, just for the record. You'd go out there and be like, oh, the cold is hard on the battery, harder for it to maintain a higher voltage. These lead acid are really good for this. So you'd have to go out there and try to cold start the car. The battery's cold, the engine's cold. It's going to be hard to get stuff turning. And the battery also generally has less power if it's cold outside. So this is what they're really designed for. So if you were to go and buy a new car, you wouldn't expect that you'd buy a car in, let's say, Arizona that wouldn't start if you drove to Montana. You'd expect to be able to go anywhere in the United States, right? So a lot of times they're designing it for this cold climate in mind. And it's a really good high power output for its size. It's rechargeable. Generally, they're actually pretty heavy though. You ever notice batteries are heavy for how small they are? That'd be the lead plates and that electrolyte in there. That's all heavy stuff. So that's a great battery, not that expensive. If you look at the cutaway, so this is your typical lead acid right here. So we've got negative plates that are coated with like a spongy lead grid. So that's lead. Positive plates, they're coated with a brown lead peroxide. So you notice we call that sometimes dissimilar metals. So it's one type of metal and a different type of metal, and then a lot of times there's a spacer in there. And believe it or not, at the most basic level, it's the difference between the two types of metals that'll actually generate the voltage. It sounds kind of crazy, but that's critical. Those are the plates. Then remember, what are we going to fill this up with? Some sort of lead acid, like an electrolyte, if you will. So when we have that whole design right there, that's going to make it so that we can charge it. It'll change the chemistry. Then when we want the electricity back, it'll change the chemistry back. It'll generate a voltage, and it'll generate actually specific voltage, which we'll cover in a bit, right? But that's your lead acid. And the thing to to understand is over time, we can get some buildup, some sulfation. These plates will actually get a coating on them from the charge and from the discharge and from time, because it's very acidic. And when those get coated, a lot of times we'll call it sulfation, the battery will no longer store the correct amount and it'll no longer put out the correct amount. And that's when it's time to actually replace it. So if this battery was pretty fresh, like let's say this one, if we were to actually, fix this hole, this cutaway, and put the correct battery acid solution in there and then charge it, this battery may actually work, because these plates don't look like they're really like sulfated, right? So let's say that we were to do that and then we were to leave it kind of discharged for a while. The longer you leave it discharged and the more time that goes by, that sulfation starts to occur and it builds up a scale and it builds up a scale and it builds up a scale, and it'll get to the point where it'll no longer really make the amount of cold cranking amps is typically what we look for. It'll no longer generate it, right? So there's two parts to worry about with the battery. One is the state of charge. So state of charge just means like when we charge it, it changes the chemistry. And the more we charge it, the more it changes the chemistry. But then when we want to make it back into electricity, that chemistry should change and change and change and change and give us like a lot of electricity. But if we never charge it that much, and let's say it's only slightly acidic, that's not going to give us a lot of electricity, right? So how could we make it store more electricity? What do you think? What would you do? Like if we were to fix this one, how could I make this one store more?
Make it bigger.
True, you could make it bigger, and then if you make it bigger, you can charge it more and more and more and more and more and more, right? So there's the charge level. The charge level is one thing. A healthy battery that's not charged all the way, it won't start the car, right? You get a brand new battery, and if you don't charge it all the way, it won't start the car. However, you get one of these batteries that has all this sulfation and buildup on the plates, this scale and nasty stuff. You could take that battery and you could charge it for overnight. You could charge it for a week. You could charge it for a month. But ultimately, when you go to start the car, it's not actually going to have enough in there to really start it, right? So that's kind of the visual. If you were to visualize this, I would probably draw it as a puddle, actually. The puddle makes the most sense to me. Let's say you walk up to a pothole. We have those around here. You walk up to a pothole and you're like, oh, you can see how deep it is, right? And you see there's only just a little bit of water on the bottom. You'd be like, oh, that pothole's not really full, right? So if you could see how deep the pothole was, and then you were to like fill the whole pothole, you'd have a lot of water, right? A lot of water to last you a long time. A lot of water. You could put a straw in there and start pulling water out of it, and you'd have plenty of water. Let's say that water is electricity, and that's what's used to start the car, right? But what if you walked up to a pothole and it was already full of water? Do you know how much water is in there? It's kind of hard to tell, right? And that's kind of the case with a battery. So if this battery is discharged, you can measure it. So if I were to grab my meter and I were to measure it, I could measure, oh, this battery is only at like 10, 11 volts, something like that, 2 volts even. I'd be like, oh, that battery's discharged. But that doesn't really tell me the condition of the plates. It doesn't really tell me if they're all sulfated and kind of messed up, right? So to really know what I have to do, I have to charge the battery. And charging the like let's say it only had a little charge down here. And as you charge the battery, it fills up. Once it's actually full, then you can tell how much water, right, is in the puddle. So this can't tell that, actually. However, a tool like this can actually more measure like the full quantity of the water. We could do it in a couple tricky ways. This is a battery tester. It's a fancy one. Cool. So when I talk about a battery for a customer, a lot of times I picture it like a puddle. I could roll up and I could measure the voltage. And if the voltage is low, I know it needs to be charged. If I put it on a charger and I leave it on the charger and then I come back and I measure it, a fully charged battery should be like 12.6 volts. And that all has to do with the number of cells. So we'll have a lot of times like 6 cells at 2.1 volts apiece. That's the typical lead acid design. So I'd be like, oh yeah, this one's fully charged, 12.6 volts. But that doesn't really tell me the depth. Make sense? That only tells me that the pothole is full. I don't know if it's a 1-inch deep pothole or like a 2-foot deep pothole. Cool? So this is very limited. Make sense? This only tells you if it's full or not. It doesn't tell you really the depth. And the reason I say that is because that's the most simple, but the more accurate is it all has to do with the conductivity of these plates and if they're all scaled up or not. And they do fail. Okay? And then if you were to look at some of these, you'll see these are still plates, but you'll notice this sort of looks like it has some sort of like a gel. It's got like a literal paste in there. So this does the same job as electrolyte, except you don't fill it up. It's not necessarily splashing around and stuff. So if it's got to go in an application where there's going to be a lot of sloshing and stuff, we probably would get away from the flooded and go to more like a gel, or we might have even a lead acid type in there too. So we got several types. Then if you were to look at this one, you see these are the caps that you could set the electrolyte level. Cool. So like I said, 6 cells, 2.1 volts. We call it a 12 volt. But if it's fully charged, do the math. What should it have? 6 cells at 2.1 apiece.
0.3. I mean,
More than that. 12 times 2.1. Let's say 12 times 2, or sorry, 6 series, 6 cells. 6 times 2 is what? Okay, good. So we got 12 as a baseline, but it's also 6 times 0.1. So wouldn't that be 0.6? So it'd be 12.6. 12.6 volts is a fully charged lead acid battery. That's how you know, right there. Okay, now that should hopefully make sense. And then within the cell, it's going to contain at least 2 sets of electrodes, so like positive plates, negative plates. And then we're just going to summarize again, lead and lead dioxide. That's your lead acid battery because the electrolyte is a sulfuric acid, H2SO4. Cool, so there's your whole lead acid chemistry right there. And then don't forget, we have those separator plates. So there is a mechanical aspect to this battery. So has anybody ever seen a battery that's like damaged, physically damaged? You can see it's messed up. Well, if you do, there's good reason to say that battery's no good, right? So if a car came in and it was in an accident and you can see that the battery's physically damaged, no good. If you are like, well, let's test it, you could test it. That battery may perform right now, but see, if you break these separators, and even if your cells aren't necessarily touching right now, that separator plate is supposed to stop the cells from touching. If the cells touch, it's actually like, it's a short. Next thing you know, you'll have a battery that has a dead cell or 2 cells shorted together. So let's say that you had that 12.6 volts on a fully charged battery, but all of a sudden it went from 12.6 to like 10.5. What do you think happened there? One of the cells, right? So batteries can fail where one cell goes bad. One cell could become shorted, one cell could, especially if the separator plates are broken. So if you get a battery that's like, you charge it for a long time, and the best you can get out of it is like a 10.5, you'd be like, oh, this battery has a bad cell. Makes sense? Got to replace that. Here's the cool thing though. The more advanced testers, they can tell. They can basically watch that voltage and be like, oh, this has a bad cell, and it'll pop right up on screen. It'll give a printout. You can give it to the customer. Hey, your battery has a bad cell. Because remember, that's our main focus. I don't expect you to design batteries. Maybe you, Tim, but nobody else. We're gonna diagnose the customer's car. So if the car comes in and they're like, hey, my battery was fine, then I went to Costco gas. This is where it normally happens. I shut my car off. I pumped gas. 3 minutes later, boom, the car wouldn't start. It was totally dead. And everybody's saying that the battery's shot. It's like, how did a battery go from good to no good in 3 minutes? If a cell just shorted out, it's done right now. Not super common, but that does happen. Yeah, and there you go. So now you can, sometimes customers are going to be sort of like, well, I want to know why. And it's sort of like, well, let's talk about the meaning of life then. But in this case, you got a bad battery. How much time are we really going to spend on this? But I could also see where you'd say, well, the battery has 6 cells. They're 2.1 volts apiece. If one cell shorts out, instantly your battery goes from 10.6 or from 12.6 to 10.5. The car won't even start with that. That battery is going to be totally shot. So now you could explain your way out of it a little bit better. Okay. And then as we talk about off of the plates, look at this. As the battery discharges, the sulfuric acid is absorbed into the lead plates, and both of the plates slowly turn into lead sulfate. Interesting. Which means the strength of the electrolyte becomes less acidic as it's absorbed into the plates. So as you charge it, it becomes less acidic. And as you discharge, it becomes more acidic. So it's kind of crazy, but it's that change in acidity, like pH actually, that gives or takes away electricity. So it's pretty crazy. Then if you were to consider that, doesn't that kind of mean we could look at the acidity level and tell if it's charged or discharged? Well, we can. We used to do that back in the day. You can check actually the pH, you could check specific gravity, you could check some things, and that would tell you if it was charged or not. And I want to skim over it, but to be honest with you, if I want to know if a battery's charged, this is going to tell me right away. It's only going to take me a second. But back in the day, people weren't really using meters on a daily basis. Let's say it was a cool old car. Pick a cool old car. It'll be our example. Older than what we were talking about, Ronnie. Give me something from like the 50s or 60s. 54 Studebaker. Yeah, when it was 1955 and that car was 1 year old, this was not what mechanics were walking around with. So I do want to take you a little bit back in time where it was like, hey, how do we tell if the battery's charged or discharged? We don't have a meter. They would actually take a sample of the battery acid and they could test it to tell if it was charged or discharged. It's kind of cool times. Now, a lot of this isn't really that critical, to be quite honest with you. Like a lot of times what's happening in the battery as far as more acidic or less acidic, like I don't even really think about. I know ways to test it, and I run with that. Now the other thing is, because we have these flooded cells, charging generates this right here, hydrogen and oxygen gas, because it separates them from the water and the electrolyte. That's cool, right? How's this look? When you're charging and sometimes even discharging, you can actually have a buildup of hydrogen gas. Hydrogen and oxygen together, that could be combustible. You know what combustible means, right? You could light it on fire.
That swells the battery?
That's what starts to swell the battery, but generally they're vented, right? So then the battery, all of a sudden it's coming out the vent. Now I want you to consider something. If it's coming out the vent right here, and I make my electrical connections, you know how sometimes they spark? Do you see how now we're concerned about that? So a lot of the safety that we talk about with the battery comes from this right here. There you are charging and charging and charging. And sometimes, let's say you put it on the charger and then you pull it off the charger and you walk over to the car, it's still going to be off gassing, right? So if you guys were to spill a bunch of gas, what's the next thing you do? Start playing with your lighter?
Yeah.
Well, let me know how that works out. Right? It's kind of the same. It's just the hydrogen gas, you know, it's not as obvious as gasoline. So you all just need to understand, when you connect a battery, we do need to be concerned about this, especially if it's hot off the charger. Make sense? Okay, so we'll come back to that. We will come.
Water turning it, hydrogen and oxygen turning into water is not a nice peaceful transition.
And when we connect the battery, make a little bit of spark right there, we got big problems. So we'll come back to that a little bit, but you have to remember that it's off-gassing that potential flammable explosion type of mixture. Okay, so here's your cutaway again. The vent caps. So this is where it vents. And also if you need to add electrolyte, this is what you'd pop off, right? So that's old school. And that's just, once again, the cutaway of the lead acid. You'll notice separator plates and etc. So it's important, let's say when we bolt this down, a lot of times there's a bar that goes across the top right here. You can over torque that and you could actually deform the battery, and you could potentially ruin your battery by deforming the plates. So understand the battery feels really strong, but actually it's not that strong. It's just in a little plastic housing.
Is that why some vehicles have like a curved bar to go over it, so if you overtorque it doesn't bend the battery.
You could still bend it though. You could still like,
Or you're less likely.
they're probably less likely, but there's no replacement for using like proper torque specs here. So you need to not over tighten this. Now I'm not going to be the torque wrench police and run around making sure you have your torque wrench, but the correct way would be to actually torque this here. Some of them have a little wedge down in the bottom. Those are kind of nicer because you're less likely to deform the battery, but the battery can't be moving around and banging into things, but it also can't be over torqued. So inside, there's going to be internal connections. So if you think about that 2.1 volts, 2.1 volts, 2.1 volts, 2.1, 2.1, and 2.1, that's like series. So in series, that would mean the negative of the first plate goes to the negative post. The positive of the first plate goes to the negative of the second plate. Sounds weird, right? And you basically in a stack 6 of them, and you can see this positive goes to this negative, and then the 6th plate, the last plate's positive goes to this terminal. So it's kind of interesting. You're basically catching the negative of the first plate and the positive of the 6th plate, and the rest of them are all kind of wired. And that's how you get 2.1 volts to go to 12.6 volts. You just wire them together, one after another, boom. But that's all done inside. Make sense? So if we were to have one of those cells shorted or, an internal open, that's why your battery can go from like good to all of a sudden totally bad, like just in the Costco gas line. Okay, and then another thing to consider, when we charge the battery, the best for the battery, the safest, the most thorough is a slow charge. You're going to slow charge it. It's not going to generate a lot of heat. It's going to slowly, you could visualize it's going to slowly pack those electrons in, when in reality, it's really just slowly changing the chemical makeup of the battery. But a slow charge can be good. If you overcharge or if you charge too fast, so that would mean you overcharge, meaning you go like to 14.9 volts or 15 or 16 volts, that's overcharge. That's going to damage the plates. Or if you charge too fast. So if you put it on the charger and you're like, forget slow charge, I'm going to put it on engine start and just blast it. And then you go to lunch and then you forget about it because somebody calls you on lunch and they're like, oh, I need you at home. And you're like, I got to go home. And the whole time that battery is getting like a major 200 amp charge, you could actually warp the plates. You could damage the stuff, but also the gas can escape, and that's specifically what they call gassing. If you ever see one that's being charged too fast or overcharged, they smell so bad. Yeah, that's it. Overcharged or too quickly charged. Yeah, exactly. That'll happen. So we never want to charge them any faster than we need to. The slower the charge, the better. Now, I will say, if the customer comes in and they have a battery concern and we go to test their battery, right? They don't care about all these stories here. They're just like, what's wrong with my car, you dumb knuckle dragging mechanic? And you're like, well, I have to test your battery. If the test is let's say inconclusive because the battery is too dead, you may have to charge it to do a proper test, which would mean it'd be great to put it on slow charge, but a slow charge may take the next 4 hours. You're going to go in that waiting room, talk with that customer for the next 4 hours. We could do a little bit of a faster charge if we have to. That's okay, but the slower charge is better. And if you charge it too fast, you're going to find out it's going to start smelling and potentially warping the plates. Okay, and then another thing is, if for whatever reason you spill battery acid, okay, I'm gonna tell you a sad story. When I was in my first ever automotive class, which is in high school, I got a brand new Carhartt jacket, the nice ones. It was tan though, mine is black now, but it was tan, it was nice. I was kind of finally fitting in with my friends because before I had like the Kmart jacket, you know what Kmart is. So I got the Carhartt, I thought it was pretty cool. Like literally the first week back from Christmas, we were doing battery work and one of the batteries spilled a little bit of acid on it and I just kind of like wiped it off. You know what I woke up to the next day? Full on holes. It like ate the material. The material was gone. So this is nasty. If this gets in your eyes, you can go blind. I mean, there's a lot of, this will totally mess your skin up. It ate the Carhartt jacket. Okay, so your skin doesn't have a chance.
This is where they tell you to make sure to wash your hands after handling acid.
Yeah, and then look, you can basically neutralize the acid with water and baking soda. So that actually provides a second cool thing. You ever seen the batteries that have like the buildup of corrosion and white chalky stuff, sometimes kind of bluish green? You could do a couple things, but the preferred would be warm water and baking soda mixed in, and you pour it on. It'll actually neutralize all that acid. It'll help you wash it. It'll turn out really clean. It costs like almost nothing. Some people also use Coca-Cola or something, and it does work. No, I agree. It'll neutralize that battery acid. It'll help to clean it really well. It does. It does. You could get rid of rust too, from what I heard. And so now look at this. This is more of the science that's important. The surface area of the plates in a cell determine the cell's current capacity. Well, that sounds good, right? So if we were to look at all the surface area of all these plates, the more surface area, the more current capacity, right? So the bigger the battery, the bigger the plates, right? So if you want to start a diesel, the battery's probably going to need to be physically larger. So if this is a motorcycle battery, it's small because the motorcycle engine's kind of small. It doesn't take that much current capacity. So what if we had something like this, but it was sulfated and half the plates no longer had like surface area that was accessible because the scale and the buildup? Now your battery's only got half the surface area, which then turns into a quarter of the surface area. Remember, this is determining the cell's current. So when you go to start the car, you may need 250, 300 amps, especially for like a V8. That battery may be rated for 500 cold cranking amps, but if you have it half sulfated, that's going to be like 250. 250 may not be enough to start it. Makes sense? So over time, as this sulfation increases and grows, the amps coming out of your battery go down. Your cold cranking amps may have started at 500, then they were 400, then they were 300, and 300s when you go out to the car and you go to crank it, and it'll be like, and you're like, oh, it started, but it barely started, huh? That battery is going to leave somebody stranded. Make sense? You think the customer even heard that sound? No. Probably not, which is why it's really important for us to do the test with this, because this is basically going to test how well they conduct electricity plate to plate. But it's a little bit more complicated than that, so we'll come back to it. And that's what I'm saying. So a lot of times our goal is to catch the battery before it leaves them stranded, sell it to them now. That way they're saving money because they're not paying for a tow truck, they're not stranded, they're not stressed out, they don't have kids in the backseat screaming and throwing chicken nuggets, which we find later under the seat, totally rotten and growing things. And so we just want to catch it now and be like, hey, your battery, yeah, oh, I've been there. Oh yeah, you give me a Sienna or like any minivan, they're in there. Oh yeah, trust me. Now those are going to turn out to be sweet kids, I'm sure. However, that's our goal though, right? To prevent that. And we can offer that as a goods and service. So if we know what we're doing and we can do the diagnosis well, we can save the customer all that, which that sometimes turns into people not understanding the technical aspect, and they say, oh, well, you should replace your battery every year. You should replace your battery every 2 years. And then it's sort of like, I could follow the logic, but if your battery is still 80%, 90% capacity and you replace it, that battery is probably $150. So we don't want to replace it all the time. Like we don't want to just keep replacing it because then you're wasting money, right? So we can actually justify ourselves by understanding how it works, being able to do the test, and then saying, hey, your battery's at 50% capacity. It's time. It's time. I've seen batteries last anywhere between, some batteries come defective, right? And so they may last no days. Other batteries can fail pretty quick because they're defective. But like a normal healthy battery, I've seen them go bad in as little as a year. 2 years is pretty typical if you're like in really cold area or a really hot area. So I went to Las Vegas and bought a Hummer H3 Alpha because it had the right engine, right? So what I really bought it for, though, it had all the suspension I wanted. So I literally went to Las Vegas to buy a truck, to drive it back, to take all the suspension out of it, put all my stock stuff on it, and resell it, okay? But I got there, and when I went to start it, and I brought a jumper. When I went to start it, it was kind of like, vroom, and it had like a really nice Optima red top battery. And I was like, man, when I saw the pictures, I was thinking I'd raid the battery out of there before I sold the truck too. Cause like the Optima red tops are like 270, 300, 320. Yeah, for me a little less, but we'll get you this discount deal. So it was like, man, and I looked and the sticker on it too was like 1 year old. And so I talked to them like, hey, has this truck been like out here sitting in your driveway? And he's like, oh, I just drove it 2 days ago. And I'm like, ooh, that battery's not sounding that hot. But then when I started it and I drove it, literally, I jumped in, started it, drove all the way down the 15. I think I made it right to my exit, got off the 15, Clinton Keith. I pulled into that. No, I got off in Lake Elsinore and pumped gas at Costco. And when I went to start it, it started perfect. And I was like, oh, maybe that battery is good. Maybe he had a draw on it, or maybe, he just didn't start it that much. So I thought I was good. So when I got home, I took all my tools out of the truck because I brought the tools. So I was concerned about a breakdown. I took the jumper out too. The next day I went to drive it to work. I went and I think I pumped gas again. So I must have stopped more in the halfway point. But I went to pump gas the next day and it wouldn't start. And it was like, it was right. So this hot weather can actually cause these batteries to have a shorter lifespan. That battery was way under 2 years old. I think it was just over 1. And I think it came with a 1 year warranty. So it was like junk. That battery was totally shot. How long could a battery last? I just replaced my Camaro battery like a month ago. And that car is a 2017. So what's that? 8 years? So I've had a battery last 1 year and I've had a battery last 8 years. So I wouldn't say you should do it every year, but I wouldn't say it'll last 8 years because it's been anywhere in between. It's really hard to predict how long they'll last. Make sense? So don't go by time. Do the actual test and then you'll know what you got.
Is it good to keep batteries on the trigger?
Amazing. The more charged you keep the battery, perfect. The more charged you keep your battery, the less acidic it is, and the longer it'll last. When the battery gets discharged, that's when it tends to grow, that sulfate tends to grow. And if it's discharged and the sulfate is growing and you leave it discharged for like, let's say 3 months, by the time you go to start, it may be sulfated and the battery might only be 6 months old.
That's what happened to my first one.
It happens quite often, actually.
Started for about like a year.
Yeah, and so now you guys are kind of understanding why the batteries act this way. And that's why we really get into the plates, because it's all about keeping the surface area clean, and that sulfation and scale growth kills the surface area, which kills your cold cranking amps. Next thing you know, you go out to start the car and the battery may show kind of charged, but it may not be able to push enough amps to start it. Make sense? And then depends on the number of plates, right? So a high-end battery will have a lot of plates. And then again, it talks a lot about the separators. And I think this, you guys should get it now, right? 6 12-volt cells should equal 12.6. So if your battery voltage is 12.6, that's fully charged. That doesn't tell you, though, how much surface area is on your plates. Make sense? So that's kind of like the puddle's full, but you don't know the depth of the puddle. If you really want to know the depth of the puddle, you can't just tell by how full it is. You actually have to measure how much water is present in that puddle. That's like this. This will measure how well the plates conduct. This effectively measures how much current. Exactly. So this can do, like, let's say that you have the puddle that's basically full to the brim, but if you start pulling water out of it, it's empty in 2 seconds because it was only this deep, right? Whereas if a battery is really healthy, you can start pulling that water out of it and it should last a long time, right? That's has more to do with like the surface area of the plates. That tool can test that. This tool can just tell you how charged it is. So that doesn't mean though, like later I show you some of the ways to test it. This is a good tool, but this doesn't tell me the surface area of the plates. This does not.
That's something running right there. It's awesome.
This, well, I'll just show you, like, this is the preferred one right here. I'm gonna pick it up for a quick second, it's heavy. Okay, this bad boy, 2-3 grand. But if it can do a lot of stuff, so we'll come back to that. That one can tell us a lot of stuff about that battery. Cool. And then Sometimes they're even getting into like a hybrid lithium ion supercapacitor. So they might have lithium ion could be like a battery, and then capacitors, if you remember way back to the beginning, they can store electricity to discharge it later. So they keep trying to come up with different technologies to work better. So if you were to have quick charge and discharge of a capacitor, that would mean like when you go to start the engine, the capacitor will just boom, provide a whole lot of amps. But then when you shut the car off, you have to keep all these computers alive to keep alive memory stored. The little lithium ion battery could do that. Lithium ion's amazing, but they do struggle a little bit to provide that really high cold cranking amps. Cool. Okay, now we'll make sure you understand the electrical capacity is determined primarily by the total surface area of the plates and their thickness. So the more plate surface, the higher the electrical capacity. Again, bigger battery, more plates, bigger surface area, more power. What are we concerned about though? Let's combine these two for now. Cold cranking amps and cranking amps. They're very closely related. They're both cranking amps. What's the difference with the CCA? Yeah, when it's cold. So if you roll out to the car and it's cold, it's going to be a little bit harder. So a lot of times we just go by the cold cranking amps. So if we do a battery test, typically we're mostly testing for the cold cranking amps. That's going to tell you when you first roll out to the car, if it's been sitting overnight, especially in a colder area, is it going to start the engine or not? That's the most important thing. If the battery starts the car, we could pretty much deal with some of the other things. But if the battery doesn't start the car's getting towed in, the car's getting jumped, right? So that's the main thing. You want to test the battery, it's going to be mostly CCA. Technically, you could test cranking amps, but we don't usually use that one. And then there's another one, reserve capacity. And technically, the reserve capacity is more like the depth of the water, actually. The reserve capacity is going to say, how long will it last? How many amps can you draw out of it before it's dead? Makes sense? So if you fully charge the battery and you hook it up to your car, and let's say your car is kind of newer and it has a lot of computers and it's keeping the clock and a bunch of memory alive on these computers, you should be able to turn the car off and walk away from it for like 3 weeks. Anybody ever leave a car for 3 weeks and have it start? That'd be normal. That's good. That's a healthy battery. That's a good way to actually test the reserve capacity. Anybody ever have a car where it's like after a week or two, it won't start? Yeah, so that may be because the reserve capacity is a little bit low. We could actually test this. That one's a little bit harder to test. Mainly the battery tester is made for the cold cranking amp, so it's always going to test that. Sometimes the reserve capacity, but do you see how they're a little different? So like if it was a deep cycle battery, it might have, a fairly low cold cranking amps, but it might have a really high reserve capacity. It depends on what we need. If it's a diesel, we don't really need a lot of reserve capacity. We need a ton of cold cranking amps. So when you go to get a replacement battery, if there's a saying in automotive, if it fits, it ships. So if you could take a battery out and put a new battery in, as long as it connects, it's good. That's not really right. That's wrong. The manufacturer who designed the vehicle comes up with a battery that has all the right specs, the cold cranking amps, the reserve capacity. They know how much all the computers draw. They know how much it's going to take to get the engine started, right? So when we go to replace a battery, do you know what we're going to put in there? The one it calls for. That's why we don't. Now, I'm not going to say you can't get away with it, but I'm just saying it's not really appropriate to be putting in different batteries and stuff, because the battery really needs to meet these requirements for that particular vehicle, which may change depending on the vehicle. Okay, now let's talk about CCA. It measures the load in amps that a battery can deliver for 30 seconds while maintaining a voltage of 1.2 volts per cell. Now, we could make this a lot more simple. How many cells are there? 6. So what's 6 times 1.2? 6 times 1 would be 6, times 2 would be, so it's 7.2 volts. I would rewrite this, but I want to show you guys how it really works, because we're assuming 12 volt systems. The reason that this is listed is because some cars have actually, like tractor trailers are 24 volt systems. So this is a test that's applicable to 12 volt systems, to 24 volt systems. A Tesla Plaid actually uses, I think it's like a 16 or 18 volt battery. So we have to specify 1.2 volts per cell. But if we were to say 7.2, this is critical for anybody who wants to go after that ASE, because it's going to ask you a question. The technician does a cold cranking amp test, and they did 30 seconds at 0 degrees, and the voltage went to 7.9. You'd have to know, is that good or bad? So at 1.2 volts per cell, that's your 7.2. So you have to have this in your mind. 30 seconds, 0 degrees, 7.2 volts. It has to stay above. It has to maintain 7.2 volts. Okay, makes sense? And we'll come back to that in just a slightly different wording one more time. All right, so then if you were to look at cranking amps, it's the same thing as CCA, but what's different? Take a look right at the bottom. And here's cranking amps. 0 degrees, but cranking amps is at 32 degrees. Yeah. So 0 degrees Fahrenheit is cold crank amps. 32 is just cranking amps. But otherwise, it's kind of the same test. We usually go by cold, just because. And then the reserve capacity would be the time in minutes that a new fully charged 12 volt battery at 80 degrees will supply a constant load of 25 amps all the way till when it hits 10.5, right? So if we start at 12.6 and we start sending 25 amps out of it, 25 amps, how many minutes go by until it actually gets below 10.5? So once it hits 10.4, hit the stopwatch and be like, all right, how many minutes was it? And that will be the reserve capacity. So if it lasts, let's say 90 minutes, that would be a 90 RC. Cool? That's a standardized test. So if they apply that standardized test to every battery, you can really understand like the actual ratings of the battery. And a lot of times, for the record, if you were to look at the battery on top, I'll even read you what this one says. It says cold cranking amps at 0, 730, reserve capacity 11. Okay, so it will provide 730 cold cranking amps, and it will provide 11 minutes at 25 amps before it drops below 10.5. That's a great battery for starting an engine. That would not be a great battery for trying to run your whole house off of with your off-grid backup system. It doesn't have a ton of reserve capacity. Did have a lot of cold cranking amps though, so it'll probably start that diesel up. Kind of makes sense. And then on the vehicle, a lot of times they'll mark either, this one didn't mark CA, by the way. This is kind of common. CCA and RC are generally going to be on all of them. They may have all three, cold cranking and cranking amps and reserve capacity. The reason you need to know that is because we want to test it, right? So how many cranking amps are good? Kind of depends on how many there needs to be, right? So if you go to the battery and it's going to say, what's the cold cranking amp rating? And you're going to type it in here. And that one, I forgot what it was it, 710 or something? Okay, I'm looking at this one and it's 730. So on this tester, I'm going to type in 730 and it's going to give it the test that's going to check for 730 cold cranking amps. If I put in 50, it's going to give it an easier test and it's going to be like, this battery's great. It only needs 50 cold cranking amps and it has 700. And you'd be like, whoa, wait a minute. Oh, whoops. I typed it wrong. I was supposed to put in 730. And then if you were to rerun the test, it'd be like, yeah, this battery's good. It's supposed to have 730. It has 700. That's great. What if it's supposed to have 730 and it has 300? That would be bad. But if you were to put in the wrong number, it would show as good, right? So you have to pull this information from the battery and put it in the machine or you're going to get an inaccurate reading. Cool. And so generally, just as a summary, there's two types of lead acid batteries. Just generally going to be starting and deep cycle. So most of the time we're worried about starting. Sometimes we're worried about deep cycle. Remember, the starting is going to be high current and short bursts. Crank the engine up, crank the engine. right? Deep cycling is going to be more like, let's say you're driving tractor trailer and you wanted to be able to maybe not have the diesel engine running, but be able to have some lights and that type of stuff. Or even better yet, like a RV or like a camper, a motorhome. A lot of times they may have starting batteries and they may have like batteries to run your lights and your accessories in the house battery. The house battery would more likely be a deep cycle to run your little things all night long, but not to start the engine. Cool. Very good. And there's a little bit of physical difference between the two, but not super critical. And the other thing is, deep cycle batteries are made to be designed, or they're made to be cycled repeatedly from like fully charged to totally dead, charged to dead, charged to dead. A starting battery, not going to be happy with that. You want to know when a starting battery is the happiest? When it's charged all the time. So like what Ronnie was saying, he likes to charge his battery on the battery tender. Leave it on there, never take it off. That'll be the happiest life you could ever give it. That's the happiest life. And they'll last the longest. They also like moderate temperatures, just like you. So like for example, the ones that are inside the car, those ones tend to have a little bit of an easier life. Unless of course you leave it outside in the sun and it's really hot, but like batteries in cars that are parked indoors in a garage, especially if it's climate controlled, they will last longer. Batteries that are inside the cabin tend to last longer, especially because they don't get quite as cold. So it's just a little bit, they're just a bit different physically, not real super critical information there. And then remember, we have to hold it down and it should never be installed without an appropriate hold down. You ever seen a battery that's just chilling there? You go over a bump and the battery can come up. Remember, that positive terminal can touch anything that's bare metal. That's the chassis ground. You're welding at that point. That's not just like, oh, it blew the fuse. The battery doesn't have a fuse. This battery has no fuse. So if this positive metal terminal touches your hood, it'll melt a hole right in the hood. Don't ask me how I know. I don't even want to tell you. I'm just letting you know, though. I used to have to drive some junk cars, too. The battery wasn't right. It was too tall. It wasn't held down. I hit a bump and literally saw sparks coming out from the hood. It burned a hole in there. All right, don't ask any more questions, though. That's true. That's true. Okay, gel batteries. So let's say this kind of looks like that Optima Red Top. A lot of times what they'll do a spiral gel mat right here. It's kind of similar to AGM, but they specifically spiral them. So that's pretty cool. You'll notice 6 of these. So this is the cell, but it's in a spiral. There's no electrolyte in here. It's absorbed goopy gel, sometimes even a mat too. And they'll have like a calcium grid for the negative, the gel electrolyte, which would be acid distilled water, and vaporized silica, which makes it the jelly. And then a calcium grid for the positive. So you notice they're using different elements. So this battery uses different elements in a different design. It's a different shape. It's totally different. The reason you need to know that, when you go to test the battery or you need to go to charge the battery, you need to tell it if it's a flooded or if it's a spiral or AGM, right? They're different. The way they like to be charged is different. Sometimes they'll call it like the charging profile. All that stuff is different. I don't even know the charging profile, to be honest with you, but they like to be charged ideally in a certain way. You know what knows the charging profile? That machine right there, that was a couple $1,000s. So if I hook that machine up, I'm like, hey, let me charge my Optima Red Top, which is a spiral gel battery. Hook it up. It says flooded or it says spiral AGM. Boom, spiral AGM, and that sucker will take care of it. Same with when I go to test it. A lot of times this will ask, what type of battery is it? It tests it different, it charges it different. Make sense? How do you know if it's a lead acid or an AGM or even a spiral? How would you guess? Just guess. Exactly. You got to examine the battery, right? So don't be like, hey, what type of battery is this? Man, look at it. What's it say? Especially these have a unique shape. Have you guys seen the Optima batteries? You can literally see the shape of the spiral. there's like individual cells. It almost looks like somebody put like D batteries in there, except they're bigger. Like if it's rounded and separated, that's going to be a spiral AGM. And a lot of times AGM and gel, they're the same really. They might be slightly different from an engineering standpoint, but for us, they're the same. Cool, so this one's pretty good. Sometimes it'll also be called valve regulated lead acid battery, but I don't really see this term a lot. And then let's see. Oh, and part of the reason is they contain a safety valve that's designed to vent internal gas pressure if it raises as much as 2. So this battery's sealed, but if it gets 2 psi built in because of overcharging or something, it'll actually pop the little valve right here and it'll vent it so it doesn't totally blow up. So we don't usually run into that, but you could if you were to really mess it up. Okay, so that should be pretty good on the gel. The other thing is it uses a lot less electrolyte. So that's kind of better, you know, safer in a lot of ways, but it's pretty chemically similar, although slightly different. And like it said, except rather than a lead plate, it's replaced with the calcium like we had already seen. The other really cool thing is it can be mounted in virtually any position. So if let's say you were to want to build a trophy truck and go do like the Baja 1000 and hit jumps and flip over and do all this type of stuff, I'd probably go with one of these. That's part of the reason the Optima red tops and stuff got such a great name, or just Optima yellow or whatever, all the Optimas, because it's like you're building a custom race car, you're building whatever, you can mount this inside, outside, right side up, upside down, over here, over there. They also withstand a lot of abuse. They're much less sensitive to extreme temperatures. So these batteries are better for those type of environments. If you're gonna try to do some off-road craziness, I probably wouldn't try to do it in one of these and imagine this acid slopping all over the place and spilling out and stuff. So different batteries for a different purpose. Okay, and then here's your AGM. You'll notice it's not, look at that for a quick second. Then look right here. Looks about the same, huh? So they may be technically a bit of a difference, but really not much. So if you look, they'll sometimes call it a sealed lead acid. So a lot of times these might not be valve regulated. They might not have the pop-off valve. They might, and then they'll use like a micropore, very, very tight woven fiberglass material. And that's the job of that, is to catch the vent gases. So we're not trying to vent it outside. That fiberglass mat is supposed to catch that. They're good, they contain more energy. And then the thing is right here, look at this, it has a lower internal resistance than gel, and they're better suited to deliver high bursts of current. So for us, we deal with them the same. For the engineering standpoint, they're like, oh, we have something that's better than the gel. We have an AGM, and this has a lower internal resistance, so you can get even higher cold cranking amps. Other than that, they're really, really similar. Higher cold cranking amps as a result of the lower internal resistance. But they do look the same, though. A lot of times the charging is the same, too. Okay, so if you were to have a gel battery, but no option on the machine, you'd charge as an AGM. Almost all the machines will have AGM listed on there. They may or may not have gel. Q, okay.
The ANG is one of the most cranking, right?
Generally, those have the most cold cranking amps. Yeah, exactly. And that's why if you roll into the parts store and you're like, hey, I want your best, biggest, strongest battery, like, oh yeah, you want one of these AGMs, because they do have the highest cold cranking amp numbers. Okay, and then you'll see there is electrolyte, but it's just enough to wet the absorbent glass mat sheets. Makes sense? So it's basically a glass mat with the electrolyte absorbed. So if you think about that, what would you call this battery? It's a glass mat with absorbed electrolyte. Absorbed glass mat. AGM. So we say AGM because we don't want to say all the words, but AGM just means absorbed glass mat. Remember the fiberglass mats, and they absorb the electrolyte. Cool. Okay, now, we mentioned this a little bit. But remember, the electrolyte acid can damage the vehicle, can damage your brand new Carhartt, can rot your skin off, can make you blind, can do horrible things. So be really careful. It's actually something that we're going to come back to when we talk about jump starting a battery and making the connections, because there's all sorts of crazy reasons why they think we do what we do, but I'm going to get you the facts. That's my job. So that has something to do with this, especially the explosion part. But remember, like, you know, PPE, gloves, glasses, all that stuff is going to be pretty important. And then if you do spill some battery acid, remember baking soda and water. That's gonna help a lot. Cool. Look right here. Remove the ground cable first, then the positive. I'll come back to that. Follow instructions for testing, charging, and connecting jumper cables. We're going to come back to that too. These are all very related. These have to do with avoiding the sparks. We want the spark to be as far away from where the gas is as possible. Okay, so I'll show you how we do that. Don't lay tools on the battery. Why do you think? Anybody ever... You don't want to lay a wrench between the negative and the positive right here? Because remember, there is no fuse for the battery. There might be a fuse in the fuse box, but the fuse is not inside that battery. So if you lay a wrench right there, it'll send all the electrons it has through that wrench. That wrench will be welding and sparking and arcing and scary. So that's why. And then generally we're going to say, don't use spark producing tools near the battery. What the heck you mean? What's that mean? Why do you think we don't want the spark near the battery? Same as these two, all relates to this. What is a spark? Yeah, we don't want to ignite that hydrogen oxygen. That's an explosion risk right there. So what's a spark producing tool? You guys ever use the old school drill? You ever use those? You do the drill and you see inside little sparks. That's power tools do that. You know what doesn't do that though? Brushless power tools. So if you have nice new brushless power tools, they don't really make sparks. But if you have old school ones, especially the ones that plugged into the cord, you really are not supposed to have those right next to that battery, especially when you think it's been off gassing. Just saying. Don't use ground cable for ignition spark tests. So we're saying, like, if we were to be testing a ignition coil or something, they don't want us to ground it near the battery, because if we're testing the spark of the ignition system and we don't have a good connection, it can make a spark right there. So we don't want a spark. Understand, it's all coming back to the explosion risk. And then again, be careful of that electrolyte. I'm going to add on here someday Carhartt jacket. I missed that jacket. It was after that point, it was like a 1 week old jacket with a big old hole in it. It was a sad day right there. And then again, like check this out. If we're going to go to do this type of work, you always need to keep in mind the sparking type of thing. So let's say non-conductive jewelry. You guys ever notice I don't wear any jewelry? I also don't have tattoos. What can I say? You don't put a bumper sticker on a Bentley. Okay, I'm just saying. I just don't. It's just not my thing. Not judging anybody. The tattoos can't get you shocked. However, the jewelry though, you gotta watch out for that one. Like if the jewelry's up here, it's probably not a thing. If the jewelry's here though, and you're working with this wrench right here, and let's just say that wrench touches the positive, right? When you're touching the wrench, the wrench is touching the ring, and next thing you know, if your ring touches the ground, all that electricity will go through the wrench, through the ring. We've seen a couple things where people have the ring like burned to their skin, and they actually end up pulling all the skin off and all sorts of gnarly stuff. Yeah, they'll call it deglove when that actually will peel off, right? So I'm not judging you or saying anything, but I also don't like jewelry. So it's kind of been like, I shouldn't wear jewelry because of this, but I really just don't like jewelry. But hopefully I never misrepresent myself, and you guys kind of know I'm off the market, but I don't wear the ring. So now you see the full justification is like scary stuff. Necklace, I'd be only worried about it if you bend like this and it kind of comes down, right? So there's some really legitimate concerns with jewelry and stuff. You know, it's a great conductor, gold. So put it on your hand and let it conduct right through there. Cool. So that's some of the reason why. The other thing, when we're doing this type of work, there's a thing we want to keep in mind. Good ventilation, because if this battery did off gas, we don't want the gas to be like in a cloud right here. And then when you make your final connection, there's a spark. Makes sense? So we want to clear it out. Picture like propane. You guys ever lit a grill or a stove or something, like natural gas? You go to turn the stove on and you hear, and then it's like tick, 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 tick. The longer the tick, tick, tick goes without it starting the flame, you know it's going to be a big poof, right? So same with this. We don't really want the gas to cloud around this. Okay, makes sense? And then the thing I wanted to make sure you understand, this is right here, this kind of sketches me out. I'm actually going to shut the one light off so you can see the color a little better. I don't like this picture. This is the red one. You know, this positive one is this is the one that's kind of scary. If you're on the positive and your wrench comes down and touches this transition cooler line or whatever this is, you know that's red positive to black ground, right? And this is chassis ground. So that right there is arcing and sparking and scary stuff. So I'm gonna give this the benefit of the doubt and assume the black cable that's over here has already been taken off. If you pull the black one first, this is no longer connected to ground, okay? Now do you guys understand why we do the black one first? If you pull the black, if this was the black cable and you were to touch the black ground to the metal, there's no problem there. I'll even show you later. You could touch the black terminal to any chassis ground, there's gonna be no spark. They're all connected, that's already the same thing. Once you pull the black one off, make sure it's no longer touching, then go for the red, and let's just say in an unfortunate series of events, your wrench touches right here, it's not gonna be an issue because this is no longer grounded because you pulled the negative terminal. Am I making myself clear? All right, so if that's clear, then you guys will understand. Actually want this one. So if that makes sense, then you guys can probably carry this to when we get into jump starting. That last connection we always want to be someplace else. So we disconnect the ground first, so that way we can't possibly short the red to any metal part. And then when we reconnect it, we do the red first, and then we do the ground last. Okay, that kind of makes sense? If you're reconnecting this and you put your ground on first, and now you're trying to tighten this bolt, you're at risk of touching something bare metal again. Make sense? Whereas if you didn't have the ground on and this wrench were to touch here, it's no problem because this isn't grounded yet because you don't have your black negative terminal on. That's the reason why. I've heard wild reasons. You need to undo the ground first because otherwise the electrons leak out. You need to undo the ground first because it's bad for the computers if you don't. You need to undo the ground first. All these made up fake stupid reasons. I just told you the real reason. It's all about risking touching your wrench to something on chassis ground. That's it. It's the only reason. It has nothing to do with computers and electrons leaking and spilling and evaporating. And I've heard some wild stuff, let me tell you. Okay? Now, and we talk about never create a low resistance connection across the battery terminals. Yeah, that's your wrench. And now you guys know extensively why you remove the negative or ground first, and then you connect the negative last when you're reinstalling, okay? And this gets into like low maintenance and maintenance free. So the low maintenance is gonna be like basically no maintenance, except if you really wanted to, you could pop the caps off. And sometimes you could check it, but it's not really made for that. And then maintenance free, it's sealed. You can't even add water if you wanted. There's no way to set the fluid level. So a lot of times this is what we're dealing with now. Maintenance free battery. So maintenance free battery means you don't have to pay anybody to check your battery on a maintenance schedule. This is not necessarily a better battery. It's not an upgraded battery. It's just like, in the interest of saving people money and having less and less maintenance, this just goes along with, well, you only have to change your oil once every 10,000 miles and you never have to have your battery fluid level checked, so it's a little bit of a marketing thing more so than actual technology improvement. Okay, and we talked quite a bit, I think, about the AGM. I think you guys are probably pretty good. And typically, for the record, if it's a full maintenance-free battery, that's going to generally be gel or AGM. If it's an acid battery, it's probably not truly maintenance free. It's probably like a almost maintenance free, low maintenance, very little maintenance, right? Because technically we could lose some water that could evaporate. Cool. Now pausing this for a moment. If you guys have a battery and you need to get rid of it, what you going to do with it? You go throw it in the trash? That's what I heard.
Yeah,
Maybe. Okay. That wouldn't be good. That'd be kind of wrong. Okay. There's bad chemicals and acid and lead plates, right? You don't want lead poisoning, correct? If you were to go and buy pipe from the plumbing store, you can buy the lead free or the non-lead free. If it's drinking water, it needs to be lead free. So lead is big problem. And you already saw the lead plates in the lead acid batteries. That'd be an issue, right? So we can't just throw it out. If you put it in the landfill, that stuff is going to seep into the dirt, and then you have what's called dirty dirt, and it's contaminated, whatever. So here's kind of a cool thing. When you go to the store and you want a battery, and you're like, oh, let me have that battery, they're going to be like, yeah, that battery's $200 plus what? The core. Now you know why. So a lot of government regulation is a hassle. I totally agree. But in some ways, it does help us. This is just because people are dumb. Okay, rework, back up. People are ignorant. They just don't know. They're like, oh, this battery, throw it out. Just junk this battery. So they'll say, okay, any parts store who sells batteries, you have to charge a core charge and you can refund it when you get the battery back, right? Mainly, it's to keep the landfills from having these bad chemicals in there. Secondary though, you know those batteries can be stripped down and they'll repurpose those. Yeah. They might just redo the battery. They have chargers that can actually basically zap the sulfation off and like refurbish that battery. I don't know how well it always works. Or worst case, they'll pull it all apart, they'll strip the lead out of it, they'll melt the lead down, and that lead will make the next brand new battery that's probably more like kind of recycled material. Showing you how to redo it?
A lot of parts.
Yeah, for sure. No, and it's legit.
The starter,
yeah, you can redo all that. The problem here, I'll be really honest, we could do that here, but the problem is we're not cost competitive. So if you want somebody to be like, hey, you know what, I'm going to hire you to rebuild batteries, it's going to be like, cool, you want $20 an hour, we need to pay into Social Security, we need to pay workman's comp, we need to pay all these things, we need to pay environmental fees for our facility, all this type of stuff. And they're like, you know what, send it to Mexico and they'll rebuild them there, send it to whatever. So other countries are doing the rebuilds. We absolutely could. It's just cheaper if we send it to them and then you roll in the store and you're like, hey, let me buy a starter. And like, I got the reman, buy a battery. And technically a lot of that battery material has probably been repurposed, so it's absolutely all rebuildable. The problem is you and me too, just too expensive. Somebody else is going to do it for cheap. So they're probably not going to live here with this cost of living. Right. So with that being said, there's two reasons, right? Environment, and also we actually want those materials. So the core charge is helpful. If you ever want to get rid of a battery, the parts stores a lot of times will just take it. They're used to having to pay people for those. So sometimes if you take it to a recycling place, they'll actually buy it. So anytime I do a battery and like Amazon, there's no core charge. So I'll take the battery. Every time I see my dad, he's like, hey, I saw that battery over there. I'm like, yeah, Dad, here's the battery. He's going to Cans Plus and he's going to get like $8. I'm like, you can have it, buddy. I'm just not going to deal with it. And I say, you want the rotors? He's like, no, those aren't worth anything. But the battery's $8. Here you go. Battery for you. Okay, so it's kind of good. There's no reason to throw it in the trash. Find somebody who's going to recycle it or you recycle it. Make sense? And so that's basically what all that slide is saying. We talk about the core charge. And then when we charge and discharge, just as a summary, remember, if when it's discharged, the active material of both plates, positive and negative, become lead sulfate, and the electrolyte becomes mostly water. So it's kind of interesting. The acid gets pulled into the plates. This is a bad situation to put that battery in. You're asking for those plates to be sulfated, okay? But then as we start to charge it, let's say we begin to charge it, basically the electricity is going to try to flow in. It's going to be kind of like an electron pump. It's going to force electrons to move from the positive plates into the negative plates. So now you have like a big pressure difference, right? When it's discharged, the positive and the negatives are kind of the same. So there's no big pressure difference. That means like if that was, let's say, a water gun or a squirt gun, you don't have any pressure. It's not really going to push the water out. It's just going to kind of dribble. But if you were to have the negative plates really negative and the positive plates less negative, they can actually build more pressure. So that's what we're doing. When we're charging it, we're actually sending the excess electrons into the negative. Okay, and that's going to build it more pressure. And then this gets into really like a lot of the chemical, but just remember, when we charge it, we're actually sending the electrons into the negative plates, and that's going to make it more acidic, and then it's going to become a little bit more like a stronger sulfuric acid. So remember how Ronnie was saying when he charged his battery, it smelled like eggs? Does that make sense? You guys know sulfur is like rotten eggs. The more you charge it, it's going to actually make that electrolyte more sulfuric, like more acidic. That's going to be a lot, it's going to be stronger, but it's also going to be like more likely to off gas and more likely to smell bad. So that was your experience. I think overall we're pretty, and by the way, when it gets fully charged, that means the electrolyte's basically as much of a sulfuric acid as it can, and that's it. It can only take so much. You can't keep charging and charging and like once it's charged, that's done. So here's why that's critical. If you were to use an old school charger, there's a timer on there. So you'd set it up for, let's say, a slow charge, a medium charge, or whatever, and then you'd set the timer, and then you'd walk away and you'd go do some job, and what would the timer do? Ding, turn it off. But I've seen some people, like, it might take more than one cycle, so I've seen some people eliminate the timer so it doesn't turn itself off. What happens if it doesn't turn itself off and you forget? You'll overheat it. It'll continue to try to charge it. It can't take any more electricity. You get the hydrogen gas. You get the really strong sulfur smell. You overheat the cells and stuff. So exactly. Yeah, exactly. So when we go to charge these, if you have an old school charger, you just have to keep this in mind. You can only charge it so much, and then you really need to chill. So we used to have a very complex lesson about doing math, how many cold cranking amps, what the voltage is, and you could do a whole calculation how long you should charge it, and then you charge it. If it's a manual charger, this is what I'm going to tell you to do. Put on a slow charger and let it charge for an hour, and then go check the battery, and if it's at 12.6, you're done. If you charge it for an hour and it's at 12.2, you can keep charging it for a little longer till it hits your 12.6 number. So you disconnect the charger and measure the voltage. If it's below 12.6, charge a little more. Now here's why we cut all that lesson out. We no longer really do that. You know what we're really going to do? We're going to hook up a charger that's a smart charger, and the smart charger is at its most basic going to monitor the voltage. And once the voltage is like pretty high and it can tell that the battery's not really taking any more amps, it's just going to shut off. And then it'll go into what's called like a float mode, and it'll just like periodically charge a little just to keep it totally full. Make sense? Or if it's a more advanced charger, it'll actually do a full diagnosis. It'll load test the battery, whether through actual load test or Conductance. It'll do a battery analysis, and then it'll, in its own system, come up with a charging strategy and be like, we're going to charge it at this, and then that, and then retest it, and it should be good, right? So that big Medtronics, that one does all that type of stuff. So if you have a battery that can be rescued, that can bring it back. But if it's no good, this will tell you too. And it might have to charge it and then retest it to tell you that's for sure bad. But that one's like a for sure thing, assuming your connections are good. Okay, so that's generally kind of what we're doing. You can see the electrons are going to be leaving during charging, and discharging, they're going to be absorbing. So it's all chemistry, really. Okay. Let's jump into get away from the chemistry a bit. Sometimes it's a little over the top. Now let's talk about temperature. Every battery has an ideal operating temperature. Cold weather, not real happy. Hot temperatures, the technically the battery performance increases, but as it gets really hot, the battery life may be compromised. So when I went and got that Hummer H3 Alpha, it was bright orange too. It was like, man, I can't buy an orange SUV, but it had the suspension. I'm telling you, that's the whole reason I went up there. When I went and looked at it, it was like a perfect example. Las Vegas gets hot. And technically in the heat of the hot, that battery would have more cold cranking amps than it ever had in its life. It's almost like it's almost like you have a horse, right? Or a car, let's make it a car. You pump it full of nitrous oxide. That car will make more power than it ever did, huh? But it might not last very long. It's kind of like that. The hot temperatures will bring out extreme battery performance, but totally shorten its lifespan. So that's, like 1 year that battery was totally shot. Okay, and so both of these are bad. Ideally, if you keep it like room temperature, that's probably gonna last the longest and also still give you the best performance. So keep that in mind. Also, the performance depends on the temperature. So when we get into this, it's gonna actually ask you what the temperature is, or in this case, you have to hold it right over this. You point this at the battery and it'll take the battery's temperature. That way when it's testing it, it's compensating for the temperature and making sure it's a really accurate test. So it's pretty neat. And then another thing is on the newer car, the powertrain control module, so the PCM or the ECM, the engine computer, a lot of times will control the levels of current flow and voltage in the alternator. So old cars didn't have this. Old cars would just charge however much the alternator made in the battery. Sometimes it was overcharged. It was safer to overcharge it a little bit than to undercharge it. So a lot of times they would just overcharge it. If you want to extend the battery life, you don't want to overcharge it. Would you agree? So a new car, the charging system becomes computer controlled. And so when it's computer controlled, it should charge the battery just right, not too much, not too little, and it should really prolong that battery life. That's part of the reason the batteries are lasting longer. The batteries aren't made better. It's that they're a little more sophisticated charging systems. Cool, so if we were to even expand on that a bit, let's say a car came with a lead acid battery and you wanted to do a cool upgrade and put a lithium iron phosphate, latest and greatest battery. You can, but the way a lithium iron phosphate battery likes to be charged is different than a lead acid, so that computer doesn't know it's a lithium. There's been a few cases where they actually will offer a reprogram for the computer to update it to a lithium. So that would be really cool if you could actually reprogram the charging strategy to be a lithium iron phosphate if you did change it. But most of the time, we just put the battery in and it's probably going to be okay. Cool, but that is one of the things to consider. Okay, and like this one, for example, has a battery temperature sensor that's molded into the battery tray. So the PCM, the computer, is actually checking the battery temperature while it's driving. If the battery's too hot, what do you think it should have the alternator do? Back off a little. Yeah, like, hey, don't charge it so much. That battery's kind of hot. Chill out a little bit, right? So some of our charging systems, have become pretty sophisticated, really all to prolong that battery life. Batteries are expensive. Cool, and they're a reliability issue too. Okay, and then again, the things that affect the battery life, especially shortening it, fully charged and deep discharge. Generally, our batteries don't like that. Unless it's a deep cycle, they're made for that. But we're not talking about deep cycle right now. We're talking about your typical car battery. They don't like this. They don't like to be charged all the way and then discharged all the way and charged all the way and discharged. They like to just be fully charged all the time. Remaining overcharged or undercharged. So overcharged would kill it. Undercharged would kill it. If you were to leave it overcharged, it's going to break it down. If you're to leave it undercharged, it's going to sulfate it. Make sense?
Damn if you do, damn if you don't.
Pretty much. But if you put it on the battery tender, those are smart enough to keep it charged just close to 100%. Not over, but not too low either. And those will really help. Also, like experiencing high discharge rates for extended period. How do you think it would experience this? How'd that happen? High discharge rates. You know what that means? Lots of amps.
So that all-
Keep guessing. Keep guessing. What's the battery's main job in the morning, remember? Battery is not happy. Whatever is making that car not start, you really need to fix it. Makes sense? So like if it's a car that's old school and it's carbureted and it's got like the carburetor jets are kind of clogged up and it's one of these things where you got to pump the gas pedal and you've seen some of those things where it's people's laughs. People's laughs, they laugh like this. Right, and you see the Mimi and you see them, they change from the person laughing to the car cranking. That's all bad for the battery. The battery does not like high discharge rates for extended periods of time. Makes sense? So if the battery's going bad, prematurely, you might have to be like, what is causing this? Is this battery undercharged? Is this battery overcharged? Is this car hard to start? Like whatever. We got to kind of know all that type of stuff. That's why this battery lesson's in depth, because there's going to be these weird ones that you have to understand what might be causing it. Another thing is excessive vibration. Why do you think this would cause a problem? Could break the plates too, inside. Breaks those plates, breaks the separators. Next thing you know, plates are touching, that type of thing. Extreme temperature, I think we're good on, right? If it's really cold, the battery literally will freeze. As you guys saw in that last couple slides, if a battery's really charged, it's more acidic. If a battery becomes discharged, it's more like kind of watery. You'd say it's more watery because the electrons go into the plates. They're no longer in the solution, which makes the solution more like water rather than acid. If it was going to be really cold overnight and you were in North Dakota, what do you think is going to survive better? Fully charged or a kind of discharged watery battery?
You say weird.
In North Dakota. If it was discharged, think about it though. The electrons are in the plates, which means the acid is now more water. What's going to happen if it's negative 27 overnight? Exactly. And if it freezes, the ice will actually break the case. That's happened. It's broken the case before. Mm-hmm.
People use things to actually defrost their batteries.
Absolutely. Okay. I was agreeing with you, and then I'm gonna say no. They actually do have battery warming blankets. I've seen those where they'll put a little blanket around the battery, and then you'll plug it into an extension cord. That would actually be smart. Not a flamethrower.
Like the heating blanket?
Yeah, just like a heating blanket. They have block heaters that'll keep the engine warm, and they'll actually jump it over to the battery and keep the battery warm. I've even seen cars that come with the cold weather package sometimes come with like a little fiberglass blanket that goes around the battery, right? So trying to keep the battery warm is good, but better to have the battery charged so it's less watery, it's more acidic. The closer it is to water, the more likely it is to freeze, right? So let's say you moved to North Dakota. First off, I feel bad. I mean, it's probably beautiful in the summer, but I'm not doing that in the winter. But the best thing you could do is keep that battery fully charged overnight. You're gonna not have a frozen one and have it break the case. And then similar with heat, and this we're a little closer to this one. Batteries don't like to be that hot. Sometimes it gets pretty hot here. So if the cooler you can keep that battery, the longer it'll last. Okay, and then another thing is dirt or moisture around the case. That can actually cause some issues. Believe it or not, if you were to look at this battery, if you were to have, right now this is clean. That means there's no path for current to flow. But if you were to have the battery kind of dirty and wet, and there actually can become a little bit of a draw across the whole battery right there, believe it or not. Especially if they're vented too, we can start to get contamination in. And then if we look into corrosion, the corrosion can become so bad where it'll actually rot or like oxidize this connection off, and then it's no good. So that battery would be ruined mainly due to the buildup of corrosion. Now, why does the corrosion occur? That's kind of normal though. If you were to get it wet, it could have some corrosion, but most of the time corrosion on a battery is when you're charging and discharging, right, it's going to make some, especially during charge, it's going to make that gas. That gas is going to try to come out, like especially if it's not vented, it might actually vent up through where this metal comes through the plate, through the case into this terminal. A lot of times a little bit of gas could come out right there, and that gas could leave little buildup, and next thing you know, it's corroding around the terminal. If it's corroding around the terminal, actually, that's probably a leaking battery case to the terminal. Sometimes what we'll do with that, clean it up really good, grease it, and then you ever seen those little, like a red and black felt donut things we put on there? Those can actually help to absorb the gases so it doesn't become so corrosive. The worst case is it corrodes and it'll damage this, but it'll actually corrode up into the battery terminal, and you'll actually ruin the battery cable, do that corrosion too. So to neutralize that acidic reaction, because that's what's causing the corrosion, clean it, water and baking soda, get that thing all cleaned up, maybe grease it, maybe put the donuts on, or maybe clean it and then replace the battery, because that's probably the source of the corrosion leaking up through the case. Cool. And then we'll take a little time to talk about different battery chemistries, although for the most part, this is not generally part of this class because it's not generally part of the ASE, but this is a battery lecture, so I want to expand a bit about it. So if we were to look at different types of batteries, here's an example, like a NiCad battery, which is nickel cadmium, or a nickel metal hydride, which is a NIM. We call this a NIM battery, or a lithium ion. And lithium ion, we're going to have to spend some time on. This could mean a lot of things. If you say lithium ion, that could mean like a lithium iron phosphate or like a number of things. So these are generally considered rechargeable batteries. This is the type of stuff that, you know, was in electronics back in the day, and then generally we've moved to some sort of a lithium and something battery on phones and modern electronics, but they used to be more like NiCad batteries if you had like a remote control car. These are all types of batteries. The reason that it will make its way into automotive is hybrid. Hybrid and EV will use this type of stuff, absolutely. Here's the NIM, for example, can have 2 to 3 times the energy density of like a nickel cadmium. So we have our lead acid, and our lead acid's great for big bursts of electricity, but with a hybrid, that's not really what we need. You know, with a hybrid, we want to be able to absorb massive amounts of electricity and then discharge, but not all necessarily in a burst. You know, if you want the car to be able to drive on electric, it doesn't just drive for like 30 seconds, right? When we crank our gas engine, like that shouldn't be going on for minutes at a time. But with a hybrid, especially even an EV, you know, we may expect that battery to be able to discharge for hours. You know, if you buy a brand new EV, you can get 300 miles of range. You're going to take several hours to drive 300 miles. Lead acid is not going to be good for that. So we don't use lead acid in those types of cars. We may use lead acid for the starting battery of a hybrid to start the engine, but a lot of times we don't even do that, right? So this is more future stuff. And then like it was saying, 2 to 3 times the energy density. Now it's an issue of not so much CCA. We're not really worried about CCA. We get into like kilowatt hours. Kilowatt hours is energy over time. So it's like power over time. If you had a brand new EV, it might be 100 kilowatt hour battery. That would mean it could put out 100 kilowatts for 1 hour, or it could put out 1 kilowatt for 100 hours. You know, it depends on how you want to slice it, right? But that's a storage quantity. Kilowatt hours is the size. 100 kilowatt hours is like, that's a lot. 100 kilowatt hours would run the average American household for like several days. Your whole house. You know you can't run your whole house off this, right? Not even close. But 100 kilowatt hour, you know, a modern, let's say it was NIM, or more likely it's going to be lithium ion, that could run your whole off-grid cabin. That's kind of why I mentioned in the beginning. So with hybrids, we need like big time energy, like massive amounts of energy. Less on a hybrid actually, but still massive compared to a starting battery. Then we get into EV. We need really, really, really hugely massive amounts of electricity because that's the only power source. And you need to be able to make it from here to Las Vegas before charging it at Las Vegas, right? So the lead acid is just no good. It's just not even remotely in the ballpark. So when we get into energy density, they're talking like in the car, we'll use the whole floor if it's an EV. We'll use a big, massive battery that's this big under the back seat if it's a hybrid. We're really concerned about energy density. And we're concerned a little bit about, like, let's say, charge and discharge. So in a lead acid, we just want to keep it charged, right? But if it's a hybrid, we need to be able to charge it and then discharge it all the way. So we change a lot of the chemistries. One of the highest would be like just lithium ion. Generically, we'll say lithium ion has one of the highest energy density ratios of common batteries and a low self-discharge rate. So that would mean like you might have, if this battery was lithium ion, it might be 10 times the energy storage than if this one was an AGM. Makes sense? Lithium ion is dense. So imagine if you could get this battery in a lithium ion, it could be the size of like a 9 volt and actually give us the same kilowatt hours. I don't know if it might be kilowatt because kilo is 1,000. It might just be in watt hours. Makes sense? So the density is a big thing. The cool thing about a gasoline vehicle is if you have, let's say it's your typical Camry, Accord, something like that. If you had a 12-gallon fuel tank, you could probably go 300 miles in just 12 gallons. If you want to go 300 miles on a battery, that battery is going to have to be like the whole floor of the car. It's going to be huge. The main problem with EVs, you know what it is? It's really energy density. So we need too big of a battery, too expensive of a battery to be able to go the 300 miles or so that people want. Make sense? However, you can see as we get more and more dense, right, and we've moved from NiCad to NIM to lithium, and now lithium's kind of further along with like lithium iron phosphate or lithium whatever. We're getting better and better energy density right there. If one of you figure out how to make a battery this big and be able to go 300 miles, you will like rule the world. I'm going to tell you right now. You will absolutely do it. Good luck. There's a lot of people working on it. And they're making small incremental changes. Especially if you can make that thing cheap, you will rule the world. Okay? Now, here's kind of the negative though. Those lithium batteries are amazing. They can be so energy dense. 100 kilowatt hours in a battery that can fit in the car. It's the whole floor though. But here's one of the problems. It may suffer from this thermal runaway. Thermal runaways. That doesn't sound that bad, right? Fire. Is fire scarier? Someone yells at, goes into a theater, kicks the door in, and they yell, thermal runaway. And you're like, what? Shut up. I'm watching the movie. You don't care. If someone kicks the door and they say fire, you're like, oh my gosh. This is like more of a technical way to say fire. So thermal runaway means it gets hotter and hotter and hotter and hotter, and it gets to the point where you can't even cool it down with all the cooling system and everything. That's thermal runaway to the point of fire. Which we wouldn't call fire, we'd actually call that a thermal event. Safer, better, more calming thermal event than fire, okay? So that's just a matter of fact. How would that happen? If a cell ruptures, you know what that means? Like pull your cell phone out, pull the battery out and stab it. You'll rupture the cell. Those two cells can short out. That battery may very well start on fire. You know that, right? So be careful about that. Okay, or what's this? Overcharging. We just talked about how we can overcharge batteries and how that happens all the time. Is this now kind of scary? It's like if you overcharge a lithium, the thing will catch on fire and burn your house to the ground. It can. So when we get into these more advanced batteries, they almost always come with what's called a battery management system. So inside, right, you can hook up to right here and here and try to charge it, but inside there's a battery management system that will, bless you, that will actually monitor the temperatures. So we'll put temperature sensors inside the battery, and if it starts to get hot, even though you're trying to charge it, it'll cut it off internally. It'll be like, nope, we're done, right? So it's actually not that unsafe because they have full battery management systems inside. This has no battery management system. You can overcharge this thing until it blows up. So separate the facts from the fear. These have the potential to be horribly dangerous, but assuming the battery management system doesn't fail, they're actually really safe. However, they're still really prone to this. How do you think a cell rupture would occur in an electric vehicle or a hybrid vehicle? Accident, boom. That's when they're sketchy. So I can tell you right now, there's a lot of collision shops. If it's an EV, hybrid mostly they'll take because the hybrid batteries are smaller and they're usually like inside under the seat. But an EV, you know, that battery's the whole floor. That's one of the first things that gets bent. If that battery looks physically damaged, a lot of collision shops, they won't even take it into their shop. They're like, nope, we're not taking that, because there's been cases where they haul in a Tesla and 2-3 days later, all of a sudden that battery ignites due to the cell rupture and the cells are shorting and it's in thermal runaway and it catches this car on fire and that car on fire and all the cars on fire and burns the whole building to the ground days later on a Sunday when nobody's there. Makes sense? So that's a matter of fact. So,
It's happened before.
oh yeah, it's happened before. It's happened in like,
I've seen that on
yeah, that's why I know. Now you guys have to know. Lithium stuff's amazing, but they're prone to cell rupture causing this thermal runaway. That's one of the negatives. So if you got a solution, I'm ears, but so far that's one of the legit challenges. Same with water intrusion. Water intrusion can short stuff out because it's somewhat of a conductor. So if these batteries aren't sealed and they're in a hurricane, next thing you know, they're on fire. And when you go to put them out, the typical EV fire can take, I want to say 10,000 gallons of water, or maybe 100. It was insane amount of water, and the water doesn't put it out. The water just takes the heat away enough to get it out of thermal runaway. So water's not even the best way to fight these. It'd be more like a type D chemical fire extinguisher. It's really a mess. But that's the fact. High energy density, low self-discharge, low maintenance, no memory. That means you can go full to dead, full to dead, full to dead, full to dead. You could also go 75% to dead, 75 to dead. If you do that on some of these like NIM or NiCads, if you never charge past 75, it will no longer really hold past 75. So you want to do a full charge and a full discharge. But on lithium, they don't have the memory. So you can charge to any amount you want, and it won't kind of lock it into that battery memory where you lose some of the usable percentage. And low internal resistance is just better for efficiency and like amperage. And then we talked about the disadvantages. Need for circuit protection to ensure current and voltage are within limits. That's that thing I said, a BMS, battery management system. So basically a lithium battery needs a little computer inside that'll control some stuff and make sure you don't overcharge it or it doesn't discharge too much. Limited shelf life, sensitivity to high temperatures. This I could tell you for sure. I put a couple lithiums in my dirt bikes and motorcycle stuff, and depending on where they're at, like if they're near the exhaust, a lot of times they won't last. They're much more expensive. Also, you know, if you look into how they're going to pull this lithium type of materials, you know, those are big, scary looking mines, and they're ugly, and they're basically raping the earth, digging huge holes to get this material. And the material, the way that they're mining it is usually big diesel trucks. There's a whole lot of issues there. But from a technical standpoint, these are amazing batteries. Do they solve everything? Probably not. And then the potential for damage if completely discharged. So again, the BMS needs to stop it from being overcharged or undercharged. If it's too undercharged, it can actually just die. And if it's too overcharged, it can have thermal runaway. So they're just not as resilient. You know, they're amazing, but they're a little sensitive. Okay, so here's an example of a lithium. You could have your basic lead acid battery that's a group 47. You want a lithium, you can go get this on Amazon. I think this was $300. I priced it just last night. You can pull your battery out. You can put this lithium in. This will weigh like 1/10 of the weight. It'll be like lighter than this one, but it'll be the size of that big one. Connect your battery terminals, click, click, and you're done. So it's a cool upgrade. Let's say you're trying to do race car stuff and people are taking out their air conditioning to save weight. You'll save more weight putting a lithium battery in than taking all your AC components out and sweating it out. Okay, that was just a dumb idea. Or you could take out all your seats and you'll probably save just as much with changing from this battery right here. These batteries could be 50 pounds. That battery right there could be like 7, so you can save a bunch of weight on this. But like I said, triple the price, sometimes more sensitivity to some of those things like we talked about. And if you notice, you can't really tell, but on top there's actually a little button right here because this has a battery management inside. If this voltage goes too low, this will shut off. And then if you want to restart it, a lot of times you actually have to put the power button on. It'll be like, okay, I'm ready to restart, but I hope you're charging me because I'm getting kind of dead, right? These also require a different type of charger and a different type of tester to be accurate and to charge it well. Cool, so they're really cool. And then let's say it's a hybrid battery. Here is your hybrid battery in the back of, based on that, that's a Prius. So it's that big. It's the whole back seat, basically. Now, the whole back seat sounds insane. That sounds like huge. It is. I mean, that's a big battery. But what's really going on in there is there's modules. So there's cells stacked. So it'd be like a small battery cell, stack. They stack them up. They put temperature sensors in there. They'll put bus bars in. And then this battery, maybe, you remember how many volts this is fully charged? 12.6, and this may be 247, 266, 231, 200 plus volts, sometimes closer to 3. Make sense? So that's a much bigger, much more expensive, much more powerful if you start to look at the amount of watt hours or kilowatt hours in there. And there's even more to this though. It gets a little bit more complicated because when we have this battery, we need temperature sensors spaced periodically. Also, right here, this is an actual blower motor. So this blower motor will turn on and it'll blow cool air through this battery to help cool it. Additionally, a lot of times here and here, there will be different voltage sensors periodically all over the place measuring each cell's performance. So like if in this battery, one cell goes bad, a lot of times there's a sensor to know that it's that cell, right? If this battery goes bad, there's 6 cells, right? Which cell's bad? Who cares? We're replacing the whole battery. This is $5,000. So it might be helpful to know that it's this cell, which might be $100. You can go in and replace that cell. Now, typically though, I'll be honest, the cells kind of wear together. So if one cell fails and it gives you a warning light, you put a cell in, that might get it down the road enough so you could trade the car in, but probably it's going to need all the new cells and that's going to be several $1,000s. Okay, but additionally in here, it has a junction block and what's called the system main relay. So I just want to make sure you guys know, this, you can't turn this off. This is the source of power. But when you're working with a hybrid vehicle, when you turn the car off, or if you like disconnect and put it in service mode, these relays make it so the electricity's inside the battery. It can't be outside the battery. So don't be afraid of working on the hybrid battery. It's only scary if you have to go inside because there's no way to turn these individual cells off. But if you're working on the whole battery as a whole, these SMRs are inside, system main relays. When the relays open, it's isolated. You could grab the orange cables and bite them if you want. As long as these relays are open, you're good. You got to make sure they're open though. There's ways to verify that. I wouldn't bite it first. I'd measure it first. And if it's 0 volts, then you could bite it if you want. But there's no reason to bite it, but you could. I'm just saying it's safe. So that's your big hybrid battery. Now you can kind of understand why this is expensive, right? And this is not lead acid. These are probably going to be, they used to actually be NIM or whatever, and then they went to lithium ion on the new stuff. I think that's probably pretty good. You want to diagnose this battery? Here's how you do it. This isn't going to help you. You go with the scan tool, and it'll actually set codes. You see this code? P0A80. You literally get like almost like a check engine light, but it'll be like service hybrid system. You hook your scan tool up and it gives you this code. And what's it say? Replace hybrid battery pack. So the whole pack, that's how you actually do it. We don't test those hybrid batteries with something like this. We don't test them with our meter. We don't measure cold cranking out. We don't do that. Because this has the battery management system, it's running its own diagnostics 24/7. It's checking, it's testing, it's watching. Generally what happens, if you just remember this, remember all those cells? If one of these cells starts to go bad, what happens is that cell will drop voltage too quick. So it'll look at all these, and each one of these cells might be 6.2 volts. And if this one's 5.7, it's like, hey, that one's too low. That's like a bad cell in a battery, right? But the computer is watching these individually. So it'll say, it might set this code, but a lot of times, this is a basic scan tool. A lot of times if you have the nicer one, it'll say P0A80, and then it might say a little number right here, 51, 26. It'll tell you which cell is actually bad. So if you wanted to be cheap, you could actually go in and replace the particular cell, but you need a scan tool that's a little higher end than this. This one's a AutoZone special here. Makes sense? So it's kind of nice. The diagnosis is simple. You all can do the diagnosis right now, I guarantee it. However, EV batteries, kind of different. Do you see this whole platform? It's a pretty cool scape. That's the whole battery. All that's the battery. That battery is from here to here, from left to right. This is cells on cells on cells on cells and cells. Now you understand? You know what the cost of this battery could be? What's up, Keon? Take a guess. 20,000 would be, yeah? $20,000 plus labor. It's not unheard to let's say you had like a Rivian or something. If you were to roll in and be like, hey, I need a new battery, they'd be like, yeah, it's $30,000 estimate. Battery might be 20 something, labor might be closer to 10. None of this is cheap. But now you can see why it's so expensive. There are hundreds of cells in this. Kind of make sense? But otherwise, the way it functions is usually pretty similar to the hybrid one. So if you look, here's all the cells. A lot of times this might not be air cooled. Sometimes they're air, but a lot of times they'll put liquid cooled in there. They'll run little radiators and coolant pipes and stuff inside, and they'll cool it. Big old battery management system. Here's the diagnosis. You want to diagnose this Tesla Model Y. You go into a special screen with a password right in the screen, right in like the center, this infotainment center. And then you go into battery self-diagnosis, and then it'll tell you, battery, the charge is 100%. It'll tell you the status of the fuse. It'll tell you generally the battery's health. See that 91%? That's pretty good, right? That's an A. So you can literally go in to a special menu on that car, and the battery management system has done its own battery diagnosis. 91% is a great number.
So can you read an estimation as to how long these batteries and Teslas last?
There's a lot of theory on that. I can tell you that the warranty from the manufacturer is 8 years, unlimited miles. I thought it was 10, I think it's actually 8. So if they give you 8-year unlimited miles, you could drive 200,000, 300,000, 400,000 miles. You're covered for 8 years, doesn't matter, don't care how many miles. However, sometimes they do fail prematurely. So if one cell fails, that kind of sucks because Tesla won't go and do one cell, they'll do a whole battery pack. Now, if you wanted to make money, you could specialize in this and you could start fixing individual cells, because I guarantee there's a bunch of battery packs. If you took 2 battery packs, tested the cells, you could make almost 2 good battery packs, but you could definitely make 1 and it'd be worth pretty good money. But generally, the only reason they'll fail prematurely is because of a defect. By design, this lithium ion, lithium whatever, depends on how it's made, right? Should last like, they'll say like 3,000 cycles or some number. They'll tell you how many cycles. How many times can you charge and discharge it? If you said 3,000 cycles, that'll last you not only 3,000 trips, that's 3,000 times you get to charge it and discharge it, and that may be 200 to 300 miles. You may get like a really long time out of this. You might, but if one cell twitches out and fails, that's really the worst part, is like if one cell's bad, it's really hard to do one cell, and not a lot of people will. So I don't know. Nobody exactly knows. I have personally seen Tesla Model S's from like 2013 with 250,000 and an original battery. One of the good indications, though, is if you look at the state of health of 91%, there's another way to translate that. It's not perfect, but it's close. If the car brand new could go 300 miles and you go to look at it used and you tell them, will you charge it to 100%? And at 100%, it'll only go 200 miles now. That means like it's lost 100 miles worth of range. That battery's not that healthy. Make sense? Now that's not the perfect, but you know, it's just showing you after a lot of cycles, they start to not have 100% of their capacity, which is 300 something miles. So if it's got less than that, you're sort of like, well,
The range will decline as the battery.
the range absolutely declines. It doesn't decline that fast, but if it's been cycled and cycled and cycled, the range will start to drop a little bit. The best way is actually to go into this screen and it'll give you an approximate state of health anyway. Cool, so this one was kind of nice. And then if you get in there, you can check different temperatures and stuff in there, but the EV battery diagnosis is actually really simple. That's why I kind of covered it first. Now, what I think we should do, you guys might be getting antsy. You want to take about 10 minutes, 15, stretch yourself out. Tim, pause me. I got you. You're hired. All right, so continuing, we'll talk about battery maintenance and service. So regular maintenance, inspection, cleaning, testing. So what do you think we mean by inspection? Yeah, mostly really looking at it. So if it was back in the day, that's when we'd actually check the electrolyte level. But on a new one, you're just pretty much like, do the terminals look messed up? You know, does it look like it's corroding? Just a visual. This is really visual. If it is dirty, cleaning it, no problem. Now testing, what do you think about that?
Check the volts, right?
You could check the voltage, but if you really want the full state of health, you got to use the fancy tester. So let's say you, who does their oil changes at home? Okay, cool. You testing the battery? No, probably not, right? And I get that, and that's true for me too, by the way. However, if you go to, I'm gonna make a punch for the dealership. If you go to the dealership, this is part of what you should be getting on your oil change. You should be getting an oil change, a multi-point inspection for those of you with me from last semester. And part of that multi-point inspection is the battery test. And if it's a good place and they're doing their job, you should get something like this printed out and you'd be like, oh, my battery state of health is good battery, okay. It's got rated for 730 cold cranking amps and it's got 632. If it's a good place that's doing like a really thorough periodic maintenance, oil change, MPI, you get something like this, that's the top of the line right there. However, Valvoline, probably not gonna happen. Jiffy Lube, not gonna happen. Independent shop, most likely not gonna happen unless they're really like, you know, trying to make it the best of the best of the best, but this is what's designed is to do a battery test. That's what's recommended. Now, how that's actually happening, I don't really know. And then the other thing is charging when discharged, and this one's always bothered me a little bit because how do we mostly charge our batteries? What charges the battery 99% of the time?
Jumper cables.
Well, we don't charge it with jumpers. So the alternator, yeah, when you start the car, the alternator charges the battery. So if a car comes in, there's no reason it should be discharged. But to change perspective, if it's your car, or let's say you're working for a fleet, the police department, if you have cop cars out back that aren't being used, yeah, part of your maintenance should be charging those batteries, right? Because we're here at the school, these cars aren't getting driven all the time. So part of the maintenance should be charging the battery. Charging the battery is going to help the battery last longer. Now you extensively understand that with the plates and the sulfation, right? See how that battery needs that type of maintenance? But for the general car that rolls into the oil change place for an oil change, that car was driven there, that car is driven more or less daily, that car's probably not going to need its battery charged. Make sense? So I wanted to really break that down. And then making sure the battery's electrolyte level is correct. Yeah, good luck with that. That's sometimes yes, but in the majority, no. We're not able to really see that. If it was a clear one, this one's amazing. I love these batteries because you can real quickly just look through the case and you'll actually see the level, you know, kind of floating there, and great. But if not, let's say it's not clear, you might actually have to pop the caps off and look in with your light. If you honestly think right now, today, that you're going to go to work and that's what you're going to do, that's just not really, that's not what we do anymore. I would skip all that and I would go right for the test using a nice battery tester, and that's going to tell me everything I need to know. Okay? At least when talking about checking the electrolyte. It's just not common. And then again, we talk about the dirt on top of the battery causing a self-discharge, that electrons can flow across the top of the surface. Just a little bit, but a little bit. Okay? Here we go. We pop the cap off and you can look down in there and see the electrolyte level. Here's one that's really dirty. You can see the electrons could actually slowly self-discharge across the top. Both of those would need, this would need to be cleaned, and this electrolyte level, if you were that far, you may need to add distilled water. Okay. And what's actually interesting, you can use your meter on top of the battery, and you'd actually set it in the dirt, and you could potentially measure a voltage difference. So if you were to have, let's say I were to use this meter and this battery, if I were to put this meter on this battery like this, and maybe we do like the black terminal goes to the negative. In fact, I could probably do it on that last screen better. If I were to put the black terminal on the negative, it's so dirty I can't tell. Let's say the negative's this one. I could put the red terminal here, 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 here. You should not have 0.2 volts. You should always have less. See that number? So if you have a 0.2 volts positive on that junk on the battery, that tells you electrons are flowing through that. So you can visualize it, yes, but you can also measure it. Okay, and making sure it doesn't, making sure we clean it, but fluid doesn't get into it, and that would be one of the negatives of this cap style. If you have dirty dirt right here, and debris and pressure washer stuff and degreaser, that could actually get down into the battery and contaminate it. So it was a love-hate relationship with those serviceable ones. Okay, and then right here we talk about cleaning the posts, and I would agree with that. So this is measuring the self-discharge. Here's cleaning the post. You ever seen a tool like this? It's like a wire brush that goes on and you clean it up. That's a good tool. Maybe put in some dielectric grease in that donut or like that piece of felt. That's going to help any of the off-gassing that occurs around the terminal get caught in the felt and not turn into corrosion. And then they also have a spray corrosion preventer. So you'd actually clean it all up. Actually, they have two. They have one that's a cleaner. You'd spray it, and it's almost like the baking soda and water type of thing. It neutralizes it and starts fizzing and bubbling. Then you just hose it off. It looks good. Then you could actually spray the protector on there, which is kind of oily, greasy type of stuff. It's similar to just putting like a silicone paste, not silicone RTV, but like a silicone grease in the donut. Just different ways to do a battery terminal service.
Just put it on top of the terminal?
Yeah, paint the terminal with that goopy grease. Okay. Absolutely. Put this little donut on there and then reclamp it. It's a good service, yeah. That one's actually good, and part of the reason is it's going to coat the metal surface. So a dielectric grease, which is silicone, it's not a conductor. It's a good insulator, but when you slide the terminal on, the terminal will make a connection between the, it'll scrape the grease and be metal to metal, but then this grease is going to prevent any sort of arcing. It also just prevents like surface contaminants, tends to reduce corrosion. These are both good services. So if you went to a decent shop and they said, hey, you need a battery terminal service, and you're like, well, what the heck does that mean? They're going to clean this, they're going to spray it, they're going to put the little felt pads, they're going to grease. That's a legit service. That's going to prolong the life of your battery. How much is it though? I don't know. I've seen them where they're $20, $25, $30. I'd say that's pretty legit. If it were me personally, if it's a family member, I'd put the 30 into it. But if it was me, you could do this for much cheaper than that. And I would probably do it right on the battery installation. So if you change your battery right off the bat, I'd probably grease this because it's brand new. You don't even need to clean it. Grease it, put the donut on there, clamp it, maybe even spray it if you have the spray. And that service will probably last the life of that battery. So if you don't want to do a good job, you just slap the battery in there. Cool. But if you want to do it while you got it apart already, I'd probably do it on the install. myself. Right, those are good things. And that was talking about that special scraper right there. So that's this tool. They have those for the top post batteries, which is what you see, but they also have them for the side post. And then this is mostly really just kind of summarizing what we did, but there's one more test we talk about with like battery maintenance, performing a battery state of charge test with a hydrometer or refractometer. Remember I was saying like on that 49 Studebaker or 50, whatever we said, 54, whatever it was, the technicians didn't have this. This wasn't really a thing. So if you wanted to tell if the battery was charged or not, you'd actually literally have to take a sample of the battery acid and you could put it in like a, you know, in one of the next slides I show it, but a hydrometer tests specific gravity. It'll float up to a number and show you the number. Or if it was the refractometer, you shine it into the light and it will show you a little mark, and that would tell you if it's charged or not. So I would like to skip for a second. This is the hydrometer right there. That's the tool I'm saying. We took a sample with this little eyedropper syringe type of thing. We can, but this is like doing something that was common like 50 years ago. You know, so it's a cool experiment. But if you ever go to a shop and this is how they're testing to see if a battery's charged, that's going to be like, whoa, there's nothing wrong with it, but it's going to be like, wow, hey, do you know what year it is? Hello? Do you have a cell phone? Like, this is old school. It's fun, actually. It's pretty cool. But why would I do a state of health charge by popping all these caps off and pulling up battery acid and dribbling it on my $100 tester? And I got this right here. Like, I can test the state of charge by voltage. What's a fully charged battery going to measure? 12.6. And so this is going to basically tell you the state of charge in a different way. You know, so it's kind of weird. But more, what I would do, this is more normal, a conductance test, which indicates the capacity of the battery and how much life is left in the battery. This test right here is way more accurate and tells way more. It gives much more information than this. This is just telling you if it's state of charge, like if it's charged or if it's discharged. You know what I'm saying? If the car just drove in, it's probably charged. This is going to tell you sulfation on the plates. That's what I want to know. Is this battery going to leave me stranded or not? You give me this test. This is a conductance tester. Okay, so we're going to come back to this and we'll explain a little more detail. But battery maintenance to me, number one would be doing conductance tests periodically to tell me what's the state of health. How much longer do I have, basically? Cool. And then, of course, we're going to do inspections. So like battery cables and terminals, those are really important. Those need to have a good connection. They need to be tight. They need to be in the right spot. They can't be corroded. A lot of times they're made of lead, zinc plates, brass, alloy, different types of alloys, right? So they're kind of special. Typically, the battery cable goes from the starting battery, and it's a lot of times a cone design. So if you guys see these top terminal batteries, I don't know if you ever noticed, but these terminals actually are smaller at the top and they get bigger at the bottom. I've seen a lot of people where they don't get the battery terminal all the way on and they just keep trying to tighten it more and more. Like what it really needs is to be loosened and driven further onto the post. And then it should need to be tightened. If you see a battery terminal that's really closed up, it's probably because it wasn't installed all the way. Okay, so it takes a little TLC to get that battery terminal clamped onto the right spot. But if it's on the right spot and you can't wiggle it, you don't want to over tighten it, but if you under tighten and you can wiggle it, that's a fail, right? So this takes a little bit more attention than you'd expect. And they probably do have a torque spec, but we normally kind of snug it up so it doesn't move and then we're good. Just make sure it's in the right spot. Okay, and then the large and the small terminal, the positive is a little bit larger and the negative is a little bit smaller. Why do you think? You don't want to switch them. If you really had a sharp eye, you could see actually right here, these are a lot heavier than they look. Okay, right here, this is a little bigger and this is a little smaller. So that's how I know this is the positive, this is the negative. It's always like that. That way you can't take the positive cable and put it on here. You'd be like, oh, it's loose. But more importantly, you can't take the negative and put it on here. If you hook it up backwards, you just let the magic smoke out of all your computers. They're not going to be happy. You could total the car like that. You could total the car on the spot like that, just so you know. Hopefully it blows a whole bunch of fuses. Fuses are cheaper than the big silver fuse. The big silver fuse is the computer itself. It's not supposed to be a fuse, people. Okay, so watch for that. There's lots of different types. These ones are common from the factory. They kind of drop down and clamp right there. This is actually aftermarket. The reason I know, it still clamps fine, but the reason I know, you see these bolts right here? Those are designed to be loosened up and have you slip a battery cable in and then bolt the cable down. That's like aftermarket. You know, somebody's repaired this before. They could be okay, but you have a sketchy connection here, and I have another potential for a sketchy connection there. I would really recommend the factory cables. I would recommend not letting your battery get to the point where the corrosion ruins your factory cables. And I would not try to break this bolt or strip this out. Like, the factory cables are the most reliable. Once you get into this, it's sort of like, I had a student just a month ago, went to start his car and it wouldn't start, and it sounded kind of like a starter, so he started doing testing and stuff, and then he's like, well, sometimes if I wiggle this cable, it starts, and he wiggles it and it starts. And first off, I was sort of like, why didn't you just tell me that, dude? Like, you already know where the problem is. I'm over here testing and testing and testing, and he's like, well, ever since I changed this cable, like, it does this and I have to wiggle it. And I'm like, well, obviously, you don't have a good connection here. And he said, what should I do? You tell me, what should I tell the kid? I agree, but I would get rid of this whole janky thing. And I told him, get a whole entire positive cable. It's going to go from the positive battery terminal probably to like your starter. Maybe it branches off and goes to your fuse box. Get an OEM factory cable, because he's telling me like once a week it kind of leaves him stranded and he's got to wiggle it around and stuff. And it's sort of like, this is like making it work. But for me, I like to make it like factory, OEM, original, reliable. Makes sense? Different types. Here you can see the positive and negative. These terminals would be actually hard to replace because you see the cable comes up like this. So that type of aftermarket clamp, it wouldn't be facing the right way. You know, they can be a hassle. If you really have a problem with the terminals, just remember the manufacturer specified correct way is to replace the whole cable, which sometimes is expensive. I'm sorry. But this is... Go ahead.
Like for example, like the batteries that have the
different adapters.
The ones that screw in instead. You know, what I'm talking about, the batteries.
The ones with a wing nut.
Yeah.
So you can grab it like this, or are you talking about the side terminal ones?
The side, there you go.
Oh, okay. So they do. This is mostly showing top, but they do have batteries that it was actually, remember that picture where that wrench was touching the ground? I told you that's why I don't wear jewelry. That was the side terminal battery. Different type, different kinds. I don't really care for the side terminals. Those are like an old school domestic thing. Mostly everything's gone to top post now. But if it asks you in the tester side terminal or top, these are tops. That one that's down on the side with the bolt that you use that little ratcheting wrench for, that would be a side. Your Escalade may have the side terminal. I bet it does. Right, so there you go. The side terminal is because it's on the side, it's flat. The part...
You're just like, oh my God.
Especially if you try to jump it. You're trying to get the jumper cable on the side, and it's like, it's kind of down there. It's hard to, these are kind of a hassle, but they were really common. Yeah. So there's a few different types, but those are the most common. Here's your side terminal, and there's a good shot of the side terminal. And then here's a flat post with a bolt through. That might actually be found on older cars. It's also found on like lawnmowers, motorcycles, ATVs. They a lot of times have this type of connection or something similar. So they have different types. This one is most likely like a garden tractor type of thing on that one. They're all prone to the same issues. Corrosion here, corrosion here, corrosion here, corrosion here, bolts, corrosion on the cable, all prone to the similar things. Now, if we look at this right here, there's a detail. Crimped on battery terminal. So if you look, the battery cable comes in, and can you guys see that shape? Remember last week I was showing you how the good terminal crimpers don't just squeeze it, they curl them over and send them down in. That's a good crimp right there. that's going to be very hard for you to replicate. So if you want to repair a battery terminal, you can, but you're going to have a real hard time making it as nice as that. You could buy a hydraulic crimper and potentially do that, but you need different dies and adapters and stuff. You're going to spend 5 times the price on the tool than you are to buy the cable. And that's why I say a lot of times we replace the cable. What's nice about this particular design though is you see this bolt? This bolt can come off, and sometimes you can change just like the clamp, the terminal end. Those can be kind of nice, but a lot of times you're going to need the whole cable if it's messed up. It's just the way that it is. Then a lot of times they'll pull heat shrink up here, and they'll kind of crimp it. Like this is a nice, reliable connection. Compare that to what we were looking at just a few minutes ago. It was right here. Like this is some backyard stuff right there. That happened in the parking lot of AutoZone. Not a fan, okay? I think overall probably pretty good. Oh, and another thing is, if you do change a cable, I don't recommend just trying to fabricate them, because those cables ran in a specific spot and they're prone to this thing called chafing, or like laying on an exhaust, getting hot. That's a cable, you'd never want that cable to be damaged, especially not short at the ground, because that's the big positive cable. That could make so much amps that it could start a fire. So I personally wouldn't try to like take some other wire and make my own and have it not run in the exact same spot. I would do an OEM factory replacement on that. Strongly recommended. Maybe not OEM, but like if it's an aftermarket, but a replicated OEM part that's going in the same spots and it's basically like a copycat of OEM, I'd go with that. I just wouldn't make something work though. You could roll into the parts store and be like, can I have a positive cable? And they'll say like, how long? You'd be like, I don't know. And they'll sell you different lengths of cable and expect you to be able to run it right and put conduit on it and put clips on it and stuff. Like, that's not a real good repair. Cool. And then also we talk about like some of the failures on cables. The actual battery cable can flex and break the wires. That's possible, but also we get corrosion on there. We get corrosion on the connectors, so we really need to talk about how to diagnose it. If the car comes in for a no crank, no start, that means you turn the key and it doesn't do the sha-na-na-na-na-na. That could be a dead battery, right? It just goes click. Could be a dead battery. Could be the starter. Could be the battery terminal connection on the battery. It could be the battery cable itself. It could be some things, right? So you got to know how to be able to really diagnose what the actual root cause, right? So talked about an open, talks about chafing, which would cause a short potentially, talks about corrosion. That all happens on cables and terminals. So how do we test the cable? Well, let's just say I were to make this a wire. If this was, now this is my phone charger, but if this was just one wire and it ran all upsy downsy and whatever, if it's a battery cable, we test it the same as when we did our board experiments. You could do available voltage in 2 spots, right? You could put your negative terminal on the negative battery and you could check what's at the positive terminal of the battery and then what's at the starter. And if you had 12.6 here and you had only 12.1 there, how many volts are dropping?
5.
Yeah, 0.5 volts, yeah. So, or you could do the voltage drop, put the positive lead here and put the negative lead here, and then you just voltage drop the cable itself. It's the same as voltage dropping a little wire on that board. It's just stretched out and one's on the terminal here and one's down there, right? But we do voltage drops on the cable. Now I want to add something though. This is a small cable. The battery cable is a big sucker, right? Do you remember how we like to do our voltage drop with the load turned on, with it active? Remember a dynamic test? The load in this battery cable is the starter. So how would we test it actively? You'd have to do the voltage drop when it's cranking. Bingo. So when you want to really do a battery cable test, you actually have to test the cable while you're cranking the engine, which kind of takes 2 people unless you have a remote start and stuff. So voltage dropping the battery terminal effectively is a little bit more involved, but it's not complex. It's simple. It's just a little more difficult is all. Okay, so that'd be a good one. And if it's got corrosion, by the way, you might be able to see the corrosion, but if the corrosion's up inside the insulation, maybe you can't see it. So, you know, if you're old school, you'd be like this, like, the battery cable's good, but that doesn't really tell you what's up in there, especially when the corrosion starts at the battery and it gets drawn into the copper cable. It might be corroded 6 inches or a foot away from the battery. You could test that with the voltage drop. And that'll tell you, hey, this cable's got more than a half a volt voltage drop, the cable's no good, period. Make sense? That's a for sure thing. Okay, and then here's one to test actually just the voltage drop on the terminal. The red lead's on the most positive part, which is the battery post. The black lead is on the positive cable. We should not be dropping hardly anything right there, right? But it would be especially a good test if you did it while cranking, because that's going to put the most demand on this. And if you were to drop, let's say 1 volt right here, that's excessive. Makes sense? So if you had a 12.6 battery, but you shouldn't drop basically nothing. Basically nothing. The less, the better. So what I'd really like to drive home on that is like, if you see a cable and it's corroded, I agree, it probably needs a battery terminal service. But if the car's in, listen very carefully, if the car comes in for a no crank, no start, you don't want to get on the phone and be like, hey customer, we need to clean your battery terminals. And they'd be like, oh wow, how much is that? And you're gonna be like $30. And they'd be like, oh great. I thought this was gonna be expensive repair, $30? Go ahead and clean it. Now you clean this terminal because it was corroded and you put it back on. What if it doesn't fix it? You call the customer back and be like, hey, so we did the cables, we did the terminal service, but it still doesn't fix it. And we found out actually your engine is locked up solid and you need a new engine. It's gonna be $8,000. You look like a ding dong. The ding dong's a nice way to put it, isn't it? So I'll even tell you some of the reason my blood pressure is probably up a little bit right now is I put videos periodically on YouTube on how to diagnose stuff, right? So I have one on a golf cart. And I admit, the guy's not good. He's my neighbor. He doesn't do a lot of maintenance. He's like a doctor or something. But he owns urgent care. So he's kind of a doctor businessman. So apparently he's smart. He's done pretty good business, but he doesn't do the maintenance on his golf cart. So you pop the seat on the golf cart and all the battery terminals are all corroded. But you know what he asked me to look at for? The battery won't, the golf cart won't move at all. It won't turn on, it won't drive, nothing at all, nothing. So my first temptation is, oh, look at all that corrosion. I could tell him, hey buddy, we got to clean all your corrosion. Cool. And he's gonna say, and that's gonna fix it. And I'm gonna say, well, I don't know, we just got to do it. That's not like when you go to the doctor and the doctor says, we're gonna put you on this antibiotic, and you're gonna be like, oh, and that's gonna make me better? And you say, I don't know. That's not how you do this, that's not how you do good business, no. So I look at it and I'm like, corrosion, noted. However, let me measure it. And I actually measured the voltage drop in the corrosion and it was dropping like 0.2 volts. That's not the issue. Dropping 0.2 volts right here is not gonna make the car not start. It's not gonna make the golf cart not move, okay? If there's a visual thing where you need to do maintenance here, cool, I'm good with that. But you gotta factor what it would really cause. Now, if I were to voltage drop this and it were to be dropping 12 volts, boom, there's my problem. Like the loss is right there on a bad connection. Then be like, hey, I got some really good news. Your whole issue is the battery terminal needs to be serviced. It's gonna be $30. And they're gonna say, and that's gonna fix it. I'm gonna say, well, yeah, because I measured it. Makes sense? I measured it, it's dropping 12 volts. 0.2, not even really out of spec. I'd still clean it as a maintenance, right? So I troubleshoot the golf cart and it turns out there's a bad charging port and the little golf cart computer thinks the charger's still connected, and so therefore it won't let it start, it won't let it move, it won't let any of that stuff. Now I post this video of how I troubleshoot it step by step and even had to bypass the charging port. And you know 9 out of 10 comments I get? The battery terminals are corroded. The battery needs maintenance. You need to clean the battery terminals. Like man, I get that. But like if all you can do is look at something and realize it needs maintenance, you're, no offense, you're worth like this much money. And then if you do the maintenance, it's still not fixed and you need someone to come in who can do the measurements and actually troubleshoot, they're worth more money. So it's up to you. You want to be worth more, you want to be worth less, but at least we get the facts straight. If there's corrosion, you can measure that. You can measure it and see like, am I gonna stop right here because that's an issue, or am I gonna continue and find the actual fault and then tell them, hey, you need a new starter. But also we should clean your battery terminals because those are messed up too, but that's not your real cause. That's just like a maintenance, right? Don't be so lame where all you can do is maintenance. That's kind of what I'm saying. Cool, so this will tell you a lot of stuff. No play, free of debris, free of corrosion, all that's good. But again, a voltage drop will tell you how bad the connection really is as a matter of fact. And there's like a really good zoomed up view, right? This is metal and this is metal, so this is a good connection, right? So we should have like no voltage drop right there. We shouldn't have any voltage drop, or very minimal anyway. Okay, why does it corrode? Dissimilar metals. So the battery clamps could be made of one metal, the post could be made of another. That's gonna cause some corrosion. They're also exposed to things like water, road salt in some areas. But probably more of the significant one I've said, electrolyte can seep out, and that'll actually cause a lot of the corrosion, like a lot of corrosion. And also if battery acid spills, like on the battery tray or on the battery cable, that acid will cause so much damage and corrosion. That's like the main reason why we have a lot of this corrosion. Cool, and sometimes you'll even see it come out like across the top of the battery. You'll see it's kind of wet between the two. That's probably battery acid that's seeped out and off gas and droplets. That's all part of good maintenance. Okay, that is ugly. That would be like, hey, this should be taken care of, right? But is that causing the no start? Maybe. Maybe yes, maybe no. How would I know? Remember that test, right? Positive terminal here, negative terminal down here somewhere. Crank it, see how much voltage is dropping. If it's dropping a lot, then yeah, there you go. If it's not, then keep looking because there's 100 cars on the road with this problem and they all start. Should they be taken care of? Yes, but we're in to really pinpoint the root cause. So measure it or treat it as a maintenance. Cool. And this is a whole entire battery being cleaned with this isn't baking soda. This is one that you spray and it neutralizes and cleans it all up. So this is kind of nice. Or you can use the baking soda and water if you want to save money. Clean it all, hose it, and then dry it. You can clean it with a brush. This is cleaning the terminal. So see, that's like a male wire brush. That's cleaning the terminal. They have a female one to clean the post. And then here is the generic replacement. Not my favorite thing, right? But if it's all clean and stuff, it can actually be a pretty good repair. I just like to go to a higher standard. You know, this is to me, if I was going to go buy a car and I open the hood, I'd be like, oh, somebody's been working on this. I want it to look like nobody's ever touched it. That's just the factory style repair that I strive for myself. Okay, now when we talk about battery charging, how do you know? Slow charging is the less stressful, better way to go. If you have the time, slow charge it. If you need to get it done quicker, you can fast charge it, but only as fast as you need to. The faster, the worse. Make sense? And then let's say if you're going to disconnect a battery, you got a couple things to be concerned about. If you disconnect the battery, the clock has to be reset. But wait, there's more. Every computer on the car that has memory that's kept alive due to the battery will be wiped out. So anybody need a smog coming up? You disconnect that battery on that car and now you try to go get a smog. They're like, hey, everything's reset. You got to go drive it. You got to drive it here. You got to drive it there. Go drive it more. Drive it on the freeway. Drive it on the road. Drive it up the hill. Drive it down the hill, right? So like consider before disconnecting the battery what all the effects are. All the computer's going to be reset. Now, if you need to do that, so be it. But sometimes you can do a memory saver and that'll like basically be a 9-volt battery jumped into the cigarette lighter or sometimes another spot or the terminals, and it'll keep the memory. But not everybody uses those. So if you absolutely need to disconnect the battery, cool, but just understand all that stuff's reset. If you're trying to diagnose the car for a check engine light issue and you disconnect the battery, a lot of that memory may be lost. Make sense? Keep that in mind. Here's the charging. Check this out. We hook up the positive, we hook up the negative. We're going to determine what type of charging rate. Let's say we can go with a slow charge. Great. If the battery's actually frozen, like ice frozen, what should we do? Don't charge it. You got to wait. Just get it to thaw out before you start to charge it, okay? And then we'll continue on that. determine some things like how many amps. This is 12 volt, 10 amp. That's a slow charge. 10 amps is slow. 50 amps, a little more medium. 250 amps is not how you charge a battery. Let's say that you're trying to do testing on the car and you need to start it, but the battery's dead. You put it on 250 volts, 250 amps, not volts, 250 amps to start it. Cool. And then you should take it off of 250 amps. You should not be leaving it. That's just to this is basically like a jump. If you want to jump the battery, you're just giving it what it needs to run. This is not how you charge it. Cool. And this one even has 6 volt settings. And then you remember what this thing is? Turn it up and then ding, and then it shuts off. Sometimes, they sometimes even have one where you can hold. I would recommend leaning on the timer because you're going to get too many things going on. You're going to forget and you're going to have a big problem. But this is old school. Has anybody seen a battery charger like this? Awesome. They're great. You need to know how to use them, but they're less common every day. Now we're going to more smart chargers that'll basically do its own testing and charge it exactly how much it wants, shut itself off. They're pretty nice. Cool. And right here it shows you how many amps are flowing. So if you were to put it on 50 amps and the battery was dead, it'll start taking 50. But as it gets more charge, this goes down, 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 and then it won't really take anymore. Cool. And this is actually measuring the voltage. So if your battery's dead, you have low volts. And as it charged, this goes up and up and up. As it gets more charged, remember the amps are going back down because it's almost full. Just normal manual battery charger stuff. And then when you're done, you want to check the battery to make sure that it charged. So this is actually showing something a little more similar to this. The state of health is amazing, but sometimes when we're just charging, we'll just check the voltage. How many volts should it have when it's fully charged? 12.6, that tells you it's fully charged, right? So you got to be able to know that. Cool, but 12.6 doesn't tell you if there's sulfation on the plates. It just tells you it's charged. Cool. Now let's say we're going to charge this Optima, an AGM, a spiraled AGM. The way we charge it with an old school charger, you can't really have any adaptation. There's no AGM setting on an old school charger. On a new school charger, like the DTAC we actually have, this has different settings. You'd put in that it's an AGM and it's going to do slightly different charging. That's going to be really good for the AGM. This Midtronics is going to ask you to diagnose, is it AGM or flooded? To charge, is it AGM or flooded? And guess what? The tester is going to do exactly what's right. That's the beauty of the new stuff. You want to know the negative of this machine? It's only one. Take a guess. Oh, it's getting heavy. It's expensive. So if I'm rolling around the shop, I don't really care that it's heavy, but if I got to buy it, $2,000, $3,000, that's a full battery diagnostic system. And they're amazing, but they're expensive. So then you get into, honestly, technicians doing battery work now, they don't really need to know much, I'm going to tell you. They could know almost nothing other than which buttons to press on the machine. The machine will tell them to charge it, the machine will charge it, the machine will retest it, and the machine will spit out a piece of paper saying the battery's good or bad. And they're like, oh, the battery, oh. Like, really basic. I'm just saying. However, the way that we troubleshoot the car, it's good for you to really understand the battery. The customer is going to have some concerns and be like, well, you tested it last week and it was good, and then it died. And it'd be like, well, plate separators can be broken and it could be shorted. The battery, this cannot tell if a plate separator is about to break. Make sense? It can only tell the level of sulfation, the level of charge, a little bit about the electrolyte, that type of thing. So I would recommend, if you just want to be basic level, you don't really need to know that much. But if you want to be like the foreman or the diagnostic technician of the shop or a little more high end, you need to be able to understand what the battery tester does, not just push buttons. Makes sense? But don't worry, AI will help you. Ask AI. Okay, so it's a little bit different. The smart battery charger is going to really do a lot of the stuff on its own. Still very helpful. 3 stages, we'll run through quick. A lot of times it'll do about 80% of the battery fairly quick, and it'll back off and then bring it to about 98% by maintaining a 14.4. And then once it's above 98%, it's going to back off a lot and do the float stage. And it's just generally going to regulate about 13.4 volts and less than 1 amp. Just a very slow charge, right? These chargers are cool because they'll do all this automatically. And this is like the quickest and most effective way to charge the battery. On an old school charger, you just do like a very slow charge, but it may take the whole day or maybe more. Cool, but that's the best way to charge the AGM. Now let's talk about jumping. If you're gonna jump start a car and the battery's frozen, you don't. That's it. You have to thaw the battery. If the battery's frozen, you don't touch it because that's one of the ones that you can cause an explosion. The other thing is, it'd be a good idea to put a load across the discharged battery. So how would you do that? You'd get like a little bulb or a little test light or whatever and completely discharge the battery. Nobody does that step. But if you read it in the book, I want to make sure I explain. Yeah, this is like, if you look at service information, a lot of times that's written by engineers, no offense. They know why it's better, but they don't realize like, if you're out in the parking lot and the car's dead, you didn't bring some wire and your lab coat and a bulb and you're gonna discharge. It's just like whatever. I would 100% skip this every day of the week, but technically I acknowledge this would be good. Get rid of any of the surface discharge and that way it's gonna slowly rise up in voltage, sure, whatever. And then when you have a jumper cable, they should have a built-in surge protector or surge protector devices. Again, I agree. Does anyone own jumper cables? They're just cables. They don't have any of this stuff. This is like from a theoretical standpoint, I totally agree. Because if you hook your jumper cables up and then you go to hook them up to the other one and you jump them backwards, those cables don't care. Those cables will burn any fuse, blow up any computer, cause all sorts of damage. Those cables don't know any better. So if you had ones that had surge protectors and jumpers and fuses and stuff, amazing. But they don't really come with that, okay? Which is part of the reason why jumper cables are old school, and I'll show you why we're doing other stuff now. I still have cables and a couple sets of jumper cables. Now this is going to be a little bit offensive, so we're going to require the use of a slave battery. And you're like, what the heck does that mean? That just means like you're going to need a second battery, and that second battery is going to do all the work. Cool? So if let's say this is the dead battery, you want to bring this battery back to life, you need this battery, and it doesn't have to be bigger, it just has to be charged. You're going to use a good battery to bring a bad battery back to life. The slave battery is the battery that's still charged. Cool? So when you pull up to a car and the battery's dead, you need to have your battery close enough, right? And you're going to hook up the battery terminals to your good battery and then bring the cables over the dead battery. And those two batteries are going to become kind of like one. They're going to start equalizing. So it's going to bring up your dead battery. And it can take, you could jump in and fire it up immediately and it might work. But sometimes it takes like a minute or two. And there's a lot of intricate details of how we want to do this. So when they say parallel, that means black to black, red to red. Now the two batteries are in parallel. So it's almost like there's two of them and they're jumped together and they're both powering the dead car now. Make sense? The live car should be pretty ready to go. So they're both going to work together in parallel, not in series. And so here are the steps. You pull up, here's the car that runs. Step 1, positive. Step 2, negative. But right here it's a little sketchy. If you put the positive and negative on this battery and those other terminals are laying like this, you know what you just did, right? You make welding. So I agree with step 1 and 2, but make sure that they're not touching. Maybe better yet, do red and red. Cool? If you do red and red, there's no chance of sparking. So do red to red, then come back over and do black on the live car. You know your final connection is going to make a spark, right? So your last connection should be, over here. Your black one should be connected to some chassis ground. Why do you think I don't want to do the last connection right there?
Magic smoke.
Close to the magic smoke, think about what might be in a cloud form around this battery. Yeah, exactly. So if we make a spark right there, and that's where that hydrogen and oxygen is, that's when you could blow one up. What's the probability? Frickin' low. technical term. Freaking low. Not impossible though. So part of the reason I watch what I say is like, honestly, I may very well connect it right there because I know my probability is pretty low. But if I talk with 20 something of you who watch another ones and another ones and another ones, and 1,000 people watch the video and 1,000 people do this 1,000 times,
One of them is gonna blow it up.
maybe, so I'm saying like the way we teach it is because of that. So if you go grab some mechanic and you're like, hey, how do you do this? And like, whatever, don't waste some time, just go right there. I never had a problem. Well, I agree. Until it is a problem. So it's one of those things where it's like, getting struck by lightning. I mean, it does happen. Not real often. This would probably be much more higher probability than struck by lightning, by the way. I have heard of this. I know of a battery that blew up, but I wasn't there. Okay, so your last connection should not be in the vicinity of the bulb of the battery. Does that make sense? That's it. So exactly how you get to that point, you could tweak it a little, but your final connection that's going to make a spark should be away. Go to the frame, go to the alternator, go to something shiny metal, and then you should be good. And it might spark right there, but it's fine. You're away from the battery. Make sense? Let me tell you how you do it wrong. Positive, positive, negative, or you could even do negative here because that wouldn't spark. But then your final negative being right next to the battery, that makes a little spark. And there's a cloud in this battery and there's a cloud in this battery. You just never want your final connection to be right by the battery. That's it. It's not even rocket science. Should be pretty good, right? Pretty simple. You could tweak a little. Now, here's what I would use. This is a modern battery jump pack. This is what's cool about them. This is a smart jump pack. So I jumped ahead a bit because this is what people are buying every day right now. This one, you can go right to the positive and right to the negative of the battery. You know why? This is not powered on until you push the button. So there's no spark. Like, see how the no spark is safer? That's why Costco's able to sell stuff like this. Costco would be a little more sketchy to be selling battery cables, but this is actually safer because you can connect it. In fact, people have connected these wrong and you go to turn on, it's like, there's no welding, there's just alarms. And you're like, oh my gosh, what do I do? Oh no, I did red to black and black to red, So this is safe. It's not powered on yet. And then I'll show you in one of the next ones, we'll show one more type of jumper, but this is a smart jump pack. These are really nice. This is a couple $100 right here. And this is the big one, it might even be more. I like it because it shows the voltage. So if you connect it to the battery and the voltage shows 7.2, that battery's dead. And then if you power it up and it brings up to 12.3, that's probably ready to start. Right there, cool. Here's the older style jump pack. So I've actually brought one, and I'll jump this battery right here. I'll do this as a live test. But Tim, you gotta let me know if you can even see right here.
No, yeah, right there.
Okay, perfect. So this is the negative terminal. This is the positive terminal. I'm gonna do a quick test. Do you remember I tested this battery? Oh, I don't think you guys saw. I tested it, I believe it was 12.3 volts. So I'm just gonna do a surface level battery test. Just the voltage. I show 12.28. So that battery's not dead, but it's not full, right? If I bring this over, I'm gonna do something a little sketchy for you. If I bring this over and I connect red to red, black to black, you notice there's no spark, right? There's no spark. Why? Because it's because this is off. So you ready? If I do this, the spark would have occurred inside, and this is made for that. So there really should be no spark, right? Because it's a switch. Make sense? See how this is safer? There's no spark near the battery. Now this shows 13.2, and I'll see if it's effectively jumping, which there's no reason to actually do this, but I'll do it for you. The only thing is, I'm kind of running out of hands. Tim, can you see what that voltage is?
12.57.
Okay, so it's coming up. And if we were to watch it, it would continue to come up. So sometimes if the battery's really dead, it does help to give it some more time. But basically, this thing is jumped right now. You could jump in and start the car. Then when you're done, turn it off and connect it. Now I'm going to show you something sketchy. All right. This is so unlikely that I'm willing to do this, but this is not a controlled experiment. So if this blows up in all of our faces, you can sue me. It didn't even really spark. You know probably why, because this battery's not that dead. The more dead this is, if you turn this on ahead of time, you might actually generate a little spark right there. You will get a spark with jumper cables, I'm just letting you know. Right, so that's why the jumper cables are a little less safe, but it's not that complicated. If this negative terminal goes over here to the frame with the jumper cable, you just make this, you make the connection over here. Cool, then you're good. Then if it sparks right here, you're like, yeah, whatever, spark a little more. I'm not scared. A little scared over here. I'm not gonna lie, I was a little nervous. Not so much for me, but just, I mean, it cost me my job, my whole career if that thing were to blow up right here. And it'd be on video, so that'd have been bad. But that's what I'm saying, probability's low, but it's not zero. So better to use something like this, hook it up, and then turn the switch on. No chance of the big kaboomy. Okay? Kind of makes sense? Now we'll set that back off to the side. I think mostly that should make sense for you. I don't think it needs any extra explanation. Here's that jump starting procedure, positive, positive, fully charged battery, and the last one, look where the connection is. It's not at the battery. It's over here on the engine somewhere, on a dedicated ground clamp, on the top of the strut, somewhere else. That one might give you a little spark, and that's fine. Okay? And then again, remember, batteries lose their effectiveness over time. The plates start to lose effectiveness, lead paste falls off, sulfation builds up, the plate material becomes deposited at the bottom of the case, and actually over time as that lead plate falls off in the bottom of the battery, it can cause a short cell to cell. I have seen that a couple times where you'll jump the battery and it will not come back up, and it'll actually make the car on the other end try to overcharge. You can feel the RPM drop and you're like, whoa. That battery's like, in fact, literally shorted because lead deposits on the bottom will short the two plates together. But typically, if we're doing our checks, we could find that it's failing before it gets to that point. Cool, so that does happen. And when they do that, the other giveaway when it's like that, if your lead plate surface has fallen off or is sulfated, there's not a lot of surface area. When you go to charge it, it'll go from dead to fully charged like really quick. And you'll be like, whoa, it charged already? Cool. But then it'll go from really charged to totally discharged really quick. You remember my claim about the puddle? If it's a shallow puddle, it'll fill up really quick, right? But it'll also empty really quick. That's like a battery that has very low capacity. It's lost a lot of its plate surface area. So what would be a better indication that a battery's good if we went to charge it? It'll take the charge and take the charge and it'll take the water. It'll take a lot of water. That means it's got a good depth. But then when you go to pull water back out of it, it should keep the water flowing for a lot longer because it was deep, right? A good battery is like a deep, deep puddle. And a bad battery could be like a shallow puddle. The reason I use the puddle is there's this thing, it's called a surface charge. So if I check the battery and the battery's low and I charge it for just like a minute and now it shows 12.6, I'm like, oh, it's full. But it's just at the surface, make sense? It's a surface charge. And if you were to turn the lights on for like 20, 30 seconds, it might drop from 12.6 to 11.2. That quick with the lights on for just 30 seconds? That tells you the battery has no depth. So that leads into one of the ways that we can do some of the diagnosis. State of charge lets us know the voltage is like really how much it's charged or discharged. You could do a number of different things. So like what you could do, you could leave the headlights on for 3 minutes. That would get rid of any surface charge. Then check the battery with a voltmeter, right? So if you were to go up to it and be like, okay, it's 12.6, turn the headlights on for a few minutes, come back, it shouldn't have dropped to like 11 something, right? That's telling you it's discharging too quick. It's got a shallow depth. Cool. A fully charged battery would be 12.6. If it's dropped to 12.4, that means you lost 25%. You're at 75% state of charge. So 25% over the course of 3 minutes, you know, that's not horrible. That's not great. But what if it dropped from 12.6 to, let's say, below 12.2? That means you lost half the battery capacity in only a few minutes. That's telling you more and more there's not that much depth to that battery. That doesn't have a whole lot of depth. It's losing the state of charge too fast. So just understanding it's going to help you do the diagnosis. You could also check your state of charge with specific gravity. With the Specific gravity is actually this one, using a hydrometer, or also specific gravity using a refractometer. Okay, so let's take a look at those real quick. If you do this test, pull some of the electrolyte, put it on the hydrometer, and then you're gonna, or the refractometer, then you're gonna hold it up to the light, or sometimes they have their own light. Do you see this shadow right here? This shadow is gonna point to something. This is coolant. Another type of, this is like orange coolant, green coolant, but look at this battery fluid, and it'll actually tell you a lot of times a percentage, and that's how you would know what the state of charge is. And you could do it like that. That was a cool way, but how am I gonna do it again? I'm just gonna measure it. Like, this is so much, I don't need to make a big old experiment out of this thing. Plus, I don't really wanna pull the battery acid out of there and spill it on stuff. It doesn't make any sense. Okay, and you could also do it with the hydrometer right here. That would point to a number. Okay, that's old school. This is new school. There you go. 12.3, you saw, you know, that's probably just like maybe 70% charged. Just right off the top of my head. They even have a chart. If you want the chart, you could get the chart tattooed right here and be like how many charge? Oh, it's 75%. It's 12.4, 75%. You could do that. But this is a little more modern right here. And you all will need to have your meters. Now, let's say you want to test a battery. This is my own custom plan. No tools battery test. Sometimes people will call and they'll be like, hey, I think I have a bad battery. That's what I would do. If it was at my house, I'd put it on the slow charger overnight. I'd just be like, hey, we're going to slow charge it. I put it on overnight. The slow charger can't overcharge it if it's a smart charger. It'll just make sure it's fully charged. Then I'll go out the next day and I'll do either a load test or I'll try to start the car. If I've charged it all night and I go to crank it and it won't even start the car, battery's dead. No meter, no hydrometer, no refractometer, no conductance tester. Don't know, don't care, don't need to. This is like a for sure test. Okay? Or the other thing I'll do is if it's not something I could keep overnight, I'll just literally go to the dead car, jump it with a jump pack or with another car, whatever. Leave it running for at least 15 minutes. At the point where it's running, what's charging the battery? Okay, so if your alternator's no good, by the way, you'd start the car and you'd pull the jumpers off, and as soon as you do, it'd die because the alternator wouldn't charge the battery anymore, right? So like,
You take what, the negative, the positive, or the negative?
I would pull the negative, and I should have the negative. Oh, no, I'm not saying like that. I'm just saying if you were to jump it, let's say I were to jump it right here like this. I jump start this battery right here. Boom, here I got it jumped, ready. I fire it up. Boom, I turn this on, I fire it up, right? If I pull this jumper off and it dies immediately, that alternator's not charging that battery. Makes sense? But if I pull this off and it keeps running, I know the alternator's working, just a down and dirty test. We cover charging systems actually next week. But if I leave it running, the alternator should be charging and charging and charging the battery. After 15 minutes, that battery should be charged enough where I should be able to shut it off and restart it. The second that I start to crank it, it tells me all I need to know. If I shut it off and I go to restart it and it goes, that battery's shot. Done. No tests in the parking lot, don't care. If I go to start it and it's kind of like, I'm like, oh, that battery's just about shot. It's half shot. Now, if I shut it off and I fire it up and it's just shutting on, boom, and it starts, I'm like, oh, that battery sounds healthy. Now I'm looking for something else. How do I know? If it started up really good though, the starter sounds good. How do I know maybe there's not something staying on that's draining the battery overnight? You ever left your lights on? Yeah. You know you're gonna come back to the car that's dead, right? There's nothing wrong with the battery. There's something wrong with the operator. That's you. There was a loose nut between the steering wheel and the seat. You connect the steering wheel to the seat. You're the loose nut. Yeah. Okay, so if you leave the lights on, the battery's gonna be discharged. It's just a matter of fact, okay? So if I start it and it fires right up, I'm like, oh, I think something might be getting left on. I think it might have what's called a parasitic drain, which we will cover, okay? So all these will give me the breakdown with no tools. However, if I were to say all that, do you think that would hold up real well in court? They'd be like, how did you test the on or about April 22nd? How did you test the battery? I'd be like, well, my experience, I start the car up, I leave it 15 minutes, then I shut it off, and that car went like this, rah, 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 room, and so I know it was good. And then I'd be like, no. Okay, so this is good. I'm letting you know what I'm doing in the parking lot. However, I'm not sure it's really professional, so I'm going to still show you the other way. The visual, right? You know what to look for. Look at the capacity ratings, and then, to really test it, it needs to be a good connection. We may need to do some basic cleanup to do a good test. And then we're going to pick how we want to test it. So the first one, I don't really recommend. It's a load test. The battery load test is going to put a load on the battery. It's kind of like if we wanted to load test your heart, we'd throw you on the treadmill and be like, run as hard as you can. We'll know if you're healthy or not. You know that, right? Once in a while, though, what may happen to a patient?
Drop dead.
Exactly. Load test, great test, except for when it kills the battery and they die. And the customer's like, hey, my battery was working. You're like, well, I load tested it. Died right there on the spot. Smelled like it was baking and everything. It smelled hot. Smelled burning flesh in there. Okay, you can kill the battery. So most of the manufacturers don't recommend this. However, I'm telling you, honestly, this is the most tried and true method. It's no different than getting you up on the treadmill. If you got a heart condition, trust me, we're going to find out. Okay. However, we might get sued, and somebody might say, I want you to pay for my battery because it was fine and you killed it. Okay. So when we do the CCAs, remember this test. I told you we're going to come back to this. The load in amps that a battery can deliver for 30 seconds while maintaining 7.2 volts or higher at 0. Make sense? And then cold cranking amps is at 32. But now, interestingly, if we were really going to try to test it thoroughly, we should warm it up. So this is a good test, but sometimes to be perfect, we should actually get it to ambient temperature. However, this is the real test, but you need to have 0 degrees. You need to have a certain number of cold cranking amps. So like if that battery was, I forget the number, 730, we should be able to apply 730. We have a slightly different test that we'd more commonly use. So here's what we're actually going to do. Half. Let's make it back to the 500. If we have a cold cranking amp rating of 500, what's half?
250.
So we're going to set the load test to 250. By the way, this is an ASE concept. To me, it's crazy that it's still on there because nobody needs to be doing this test anymore unless you want patients dying on your treadmill. However, test at half CCA. So that'd be 250 on a 500, right? How long? Again, half, 15 seconds. So if you do half for 15 seconds, if it's a pass, it's 9.6 or higher. If it's a fail, it's less than 9.6. So if you get a 9.5, that would be a fail, right? If you got a 9.6, that'd be a pass. If it only dropped to 10 volts, that's a really good pass, or that's an okay pass. If it only dropped to 11.7, that's a great pass, right? So this is the true cold cranking amp test. You'll notice, and this is generally at roughly at ambient temperature, like room temperature, 68, 70, right around there. This is how we actually test it. You notice it's slightly different than the full rating though, right? So we're not testing it to the full rating for 30 seconds and all the way down to 7.2. We're doing like a slightly less harsh test with a little bit looser passing numbers. So half the CCA, 15 seconds, got to be 9.6 or higher to pass. For whatever reason, the ASE still asks that almost nearly exact same question. Cool. Then, if it fails, what we should do is we should do a further test. A lot of times we won't, but what we should do, we should slow charge the battery to 100% state of charge, because do you know it can fail this test if it's not all the way charged? This is why this test is a hassle. This test doesn't account for if the battery's at 90% or 70% state of charge. This is assuming it's totally charged, okay? So what we should do, we should charge it all the way, slow charge, 100%, and then do the same load test again. And if it fails, then we need to replace it. And if it passes, then we need to figure out why wasn't it charged. Does this sound like something you could do in like 10 seconds?
No.
At least 1 minute? Okay, and that's why we don't do that. We do this. This is going to give us similar results, but the load test is the 100%, like it's always accurate. And this is walking you through. So hooking it up, half of the CCA, that's what we're going to set the machine to. So this is old school. You could tell this is old, right? Right here, the old school technician is setting the knob to how many CCAs. This is basically like a big toaster. You're going to make that battery send a whole bunch of amps through like a toaster grid, and they actually get hot and they smell, and it's, I don't know. This is like, people who worked with this old stuff have memories of this, and they'd be like, oh, the smell of the whatever version this machine is. They have names, I don't even know. I'm showing my age now, which to you is old, but to people who know this stuff, they're like, you're such a baby. I never really used this old fine equipment. Fine equipment, that's what I was gonna say. So you could set it right, they would smell, and they'd be like, oh, the smell of burning sun load testers and grease and oil. And I'd be like, don't know, never smelt it, don't know. But this is, oh, it's the VAT 40. I do see some of these kicking around. They had the VAT 30s, and this is old, right? Set it to half the CCA. What was half the CCA in our example? They used to do some other stuff, but this one's just a tester. So in ours, it'd be 250. In the other example, it'd be 700. Half of that would be 350, right? So like, you manually set this. You have to know. You have to know. On this newer tester, you just have to push buttons. So this did require a little more knowledge. Now here's more realistic. We got the Midtronics. This is basically an offshoot of this one. Can you tell how similar they are? Same brand, Midtronics. This one was specifically for the Honda dealer. Every Honda dealer has to have this. They have the new version now. But every dealer has to have this, and that way, when the car comes in for the oil change, you hook this up and it gives a little printout, and that printout is supposed to be on every oil change they do. The dealer is not here to save money. You know, it's not cheaper, but they're trying to justify we do more when we do your oil change in MPI, whereas another place takes the drain plug out and they put it in, change the filter, put oil in. We're telling you if your battery's gonna fail, they're shooting for a higher standard, cool? So every car got tested. And the reason they justified it, you could do this whole test in under 60 seconds. Clip, hook it up, tell it how many CCA, push the button, and guess what? This measures volts too, so it can know the state of charge and it can calibrate the pass-fail results, accounting for a state of charge that's less than 100, right? You shouldn't really need to charge it all the way up and take all day. Cool. And then if you look, a lot of manufacturers require this tool. And if you find a battery that's bad under warranty, you know what they want? They wanted the slip back in the day. You'd have to print that paper. So if you didn't have this paper, Honda, for example, in this case, would not pay for a replacement battery for the customer. You understand the dealer doesn't pay for that. The dealer provides it, and then Honda pays the dealer for the battery they provided. Makes sense? Without this, Honda ain't not gonna pay the bill. So can the VAT 40 do this? No, the VAT 40 gives you smells and it gives you a guaranteed test, but there's no proof that you did it. So this is gonna be more preferred by the manufacturers. But wait, there's more. When we do that test, it's how it really works. And there's a couple more things I'd like to say. This is old school. This newer one can get you the slip, but it also gets you like a number that has to get put in the computer. And so now you don't have to print the slip, because the slips would get lost sometimes and the printer didn't work and you'd freak out. Now it gives you a number and you write the number down on the repair order, and that tells you, you don't know what the number means. It's like ABC XYZ 1237882XY. You write that down, but the manufacturer can put that number in and it'll tell them the information, and then they can approve or decline. Make sense? So this is the ticket, but here's how it works. I'm gonna skim this. The conductance tester, think about it. You can't really check resistance of a battery. Remember when we check resistance, you have to turn the system off. You have to isolate it, right? You can't isolate the battery. The battery is the source of power. So you can't isolate it, so therefore you can't test resistance. Does that make sense? Oh, but you kind of can. If this uses AC current, you can send alternating current through the plates and basically test the resistance or the conductance of the plates using AC, even though they're live with DC. So that's what this does. This measures the resistance of those plates. If they're all sulfated, what do you think it's going to measure? Resistance numbers, give me. If something's corroded, what's the resistance? High, exactly. So if these are sulfated, that's corrosion. The resistance is going to be high. That means the conductance is going to be bad. It's going to have a bad CCA. So this measures the internal resistance using ASE, and it spits out a CCA rating, and you don't have to charge it, you don't have to discharge it, you don't have to time it, you don't have to set the stopwatch. It just gives it to you on the spot. So this is the future here. Well, it's not even the future. This has been the go-to for like 20 years. So I don't know, the book's kind of funny sometimes. They want to talk about that VAT 40, but you probably aren't even going to see one of those old testers. You're going to see these. Now this one's even more advanced, and at this point I'm going to slide it on over and you'll at least get to see a bit of it. So this has got, I'm going to pick it right up. Don't you even worry about this. Okay, this tester, all right, make some room. It's a big girl. If you guys could see, there's some big cables right here. See how big these are? This is the charging part. But then there's some smaller cables and an amp clamp. There's all sorts of little stuff here. So now I'll pull it back down so you guys can see. It does a lot of stuff. If we want to just test the battery, we can actually pop this off and I can undo this. Cool. It's not that different than the other conductance tester, but I pop this off and then the battery cables are a little bit tangled up. So I just got to fish them out. Okay, you are coming with me. And you, actually it's going to be a little bit hard to get them out, so I'll just show you the other end. These cables are small. Okay, if you ever roll these cords up like this, you're so fired. This is a tangled up mess, which I didn't catch. Okay. Okay, see how these are smaller cables? You hook these up, this does the test. If the test is like the battery is low state of charge, you'd pull those cables off and you hook these big ones up, and this will do what's called a diagnostic charge. It'll charge it at the correct amount to get the state of charge to be 100. You can leave both cables on. When it's done charging, it'll do a retest. And that's what this thing's notorious for. Charge and retest, charge and retest, fine. So it'll do this whole diagnostic cycle where it'll test and then it'll charge and then it'll retest and whatever. And the result is it's very similar accuracy of the load test, but it doesn't kill the patient on the treadmill. Makes sense? So this is a tool that you guys will probably see a version of this. This one's the Toyota one. GM has their own. Honda has their own. So they're all using something like this, and this generates the codes. It does the chart. It does all that stuff. And additionally, what's kind of cool, I think I have it. You'll see that's why it says a battery system analyzer. It analyzes more than just that. But if you also look, it can do jump start, and it can also do this thing called a power supply mode. And what that'll do is keep the voltage very, very steady, like perfectly steady. Like let's say it was 13 volts, it would be 13.0 the whole time. That's very helpful for, what's this mean? If you're gonna do like computer software updates, reflash the computer, you know if your voltage drops too low, you'll brick it, right? Brick the computer, it'll just die. It'll be like when it's doing the file and it's installing it, it's almost like if you're installing a file in your computer and you just rip the cord out of the wall. It's not gonna be happy. So that can happen with the battery. If your battery voltage falls off too quick during a computer program, it'll ruin the computer. But if you hook it up with this and you do power supply, it can keep it going indefinitely. Makes sense? So on a modern car, this type of thing is going to be critical for accurate diagnosis, for good charging, for the full diagnosis of the battery system, and for reprogramming. So this battery charger is something we're going to use a little bit later. And then another thing to keep in mind is, again, when we disconnect the battery, that's going to affect all sorts of modules. We talked about one with the, you guys ever seen the car where you open the door that's frameless and the window drops down a bit? Then when you close it, it closes and then it goes up a bit. You ever seen the cars where you put the window down by press and hold and it goes all the way down? And then if you press and hold up, it'll go all the way up. All that stuff relies on that memory. So if you disconnect the battery, those are lost. So you may have to do something that's called initialization. Like with the windows, a lot of times with the windows, you'll actually hold up for like 20 seconds or 10 seconds or something, and then hold down for a certain amount of time, or then you might pull up and then push down. There's a little procedure you have to do to reinitialize these types of things. So that's one of the reasons we don't like to disconnect the battery. And if we do, we could use the memory saver, which is just another way to jump in and hold the memory. But realistically, eventually you're going to have to replace a battery, so it's getting disconnected. You have to be able to go in and look at which modules need to be like reinitialized and reset basically. Okay, and if you don't, we've had people they get their battery changed by O'Reilly's in the parking lot, and then they're like, hey, my automatic up and down windows no longer work. I think they fried something. No, they just didn't do the reinitialization procedure. So you'd have to look on service info and see reinitialization. It'll say like, after you disconnect the battery, reset the clock, redo this, redo that, reset this thing. That's what I'm kind of saying. And sometimes it's even security system stuff. It could be a bit of a pain. But it is what it is. If you were to use another battery like that jumper, technically, you could use that jump pack and go right to the cables and then disconnect the cables from the battery, but those cables would still get their power from the jump pack, and you could maybe skip the reinitialization, but that could be a bit sketchy too. So just so you know. And then the final thing is parasitic draw. So does anybody know what a parasite is? What does it do?
Leeches off something else.
Exactly. It's a little leech. It's a little moocher. It's a parasite. Parasitic drain, what that means is you shut the car off, all the computers should shut down, right? And it shouldn't really draw too much electricity. But if it has a parasitic drain, what that means is like something is drawing too much. Something's leaching off of that battery. Something's killing that battery. So I'll give you an example of a parasitic drain so you understand. Most simple, you guys ever turn the dome light on or like the interior lights and forget about it? You turn the lights on, you do your thing, you get out, you close the door, the dome light's still on. What's going to be the status of the battery in the morning? Can be dead. That's a parasitic drain. A parasitic drain could be as simple as a light's left on. The light that's left on shouldn't be that hard to diagnose. You jump start the car, you charge it, and you're like, hey, the dome light's on. That's the problem. Click, turn it off. I fixed it. But other times it could be complex. It can be a computer that's waking up. I had one, the flip down visors. You ever seen the visors where you flip it down and then you flip the little thing to see the mirror and it has a light? I had one of those. The customer didn't tell. I mean, they probably knew, but the little cover that you flip up was broken off so the lights were on. But then when you fold the visor up, the lights are on, but facing the headliner, you couldn't see it. So I had a car came in, dead battery. I jump it, I leave it running 20 minutes, I shut it off, I restart it, the fire's right back up. Does it need a battery? No. Could I test it with this? Sure, and I did, at least in this story. The battery tests good. Do not sell the battery. That's not going to fix the car. Now, if I put a brand new battery and I'm going to start it and be like, yeah, it's good, right? I'm going to give it to them. What's going to happen the next morning? It's going to be dead again, and they're going to be like, you don't know what you're doing. You're an idiot. You're fired. Like so easy a caveman can do it, right? So the fact that the battery's good means it's not the battery. So I'm thinking like, I think it's got a drain. Now I'll show you how to measure that, but I did the measurement and it was way excessive. It was way too high. I could see how many amps were leaving the battery. I'm like, oh, that's way too high. But where is it? And I start looking and I'll explain the procedure. But basically, I go to the fuse box and I pull a fuse and look at the number. And if the number is still too high, it's not that one, I put it back in. And eventually I pulled a fuse for the interior lights and the number dropped. And then I plug it back in and the number spikes. And I pull it back out and the number drops. What's it tell me? Where's the drain? In the interior lights. Yeah, so we do our diagnosis from the fuse box. And once I saw it was the interior lights, then I'm like, okay, let me look at all the interior lights. And that's sure enough, when I flip the visor down, I'm like, oh, the plastic cover's broken off. Was that an easy diagnosis? That's not really. How long you think that took? That took me like at least 30 minutes. And the customer's like, oh yeah, that plastic thing's broken. And I'm sort of like, well, if you said so, I would have known it. But see, when you give it to me as a parasitic drain, and I test the it probably took a solid hour. Test the battery, test the drain's excessive, wait for stuff to go to sleep, start pulling. It was actually, took me some time to find it. It wasn't real complex, but it takes time to find it, right? And that's what we're doing when we're doing this parasitic drain. So if you were to look at the drain, for example, it should be 75 milliamps or lower. Like a lot of cars were 23 or 50, but 75, not amps, milliamps. This car had like 750 milliamps. Like it had 10 times what it should have had. Computers being awake, or generally computers keeping their memory alive, should drop it down to this type of number. It should not be 750. 750 means something's staying awake that shouldn't be, or something's on, something's drawing, right? So that was my clue. It was way excessive. And then when we go ahead and do that, it can take some time, right? So we'll show you like this way. When we turn the car off, it takes a while for all the computers to go to sleep. When they're awake, they draw way too much. That's normal. But slowly but surely, they'll go to sleep, go to sleep, go to sleep. It may take 30 minutes, sometimes more. But by the time they should all go to sleep, we got 50 milliamps. That'd be a pass. Okay, but the problem was I did the test because I knew the battery was good, but it was still dead, so I knew something's on. And I had 750 milliamps, and I'm like, oh, that's the fail, right? Now, how's this hooked up? Look, we disconnect the negative terminal, and we send the negative terminal through the meter, and then we send the lead to the chassis. So if you think about how electrons flow, conventional, they go to the positive, they go do a bunch of work, right? Then they all come back on the chassis and they all go through this cable. But rather than this cable go into here, now I'm forcing it to go through the meter, just like how we measure amps, right? Just how we measured amps on the boards, you measure parasitic drain the same because you're measuring in amps. But you're not looking for amps, you're looking for like milliamps, right? So you're looking for not dollars, you're looking for pennies, but you're still counting the money the same way. Make sense? Every electron that goes through here now has to go through the meter and be counted. 1, 2, 3, like that. Cool? You could all set this up. It's not hard. But when you set it up, then you might have to wait 20 minutes for everything to go to sleep, and eventually you should get a number like this. And if you do, it doesn't have a drain. Right? But in my case, it did. Then at that point, if I can see it's too much, right, the next step would be go to the fuse box. And I think I've got that one right here. And you could start pulling fuses. So if we were to pull that 10 amp fuse and it were to go away, I know that it's related to that circuit. Make sense? So this is like your main diagnostic point. Otherwise, you got to go around and check all sorts of stuff. Whereas if you pull the fuses, every circuit's going to be right here. Now the problem is you got multiple fuse boxes in the new cars. So it gets much worse. And also, this method, remember that we're fused right here. You know how many amps we can pull with the meter, with it on the big A slot, right? Remember? 10 amps. On a new car, when you try to, when all the modules are awake, it's more than 10 amps. So actually on a new car, you can't do this anymore. But the theory's there. The way we have to do a new car, inductive amp clamp. So this was a good method. But now that the cars draw so much, because they might have 40, 80 computers, that's going to be more than 10 amps. I'm letting you know. Now we got to do inductive. This amp clamp goes around it, and it measures how many amps are leaving. This is actually easier, but this tool costs money, so that's why it kind of sucks. We put it on there. We measure how many amps. Then we'll go to the battery, and we'll do the same. We'll go to the fuse box, and we'll do the same thing. Pull fuses. But how many fuse boxes on a modern vehicle based on what we did in the beginning of the semester? 2, 3, 4. So if you open a door to get to the interior fuse box, you know what it causes? All the modules are awake. They're like, hey, they opened the door, get ready. They might turn the car on. Everybody, wake up, wake up. And then all of a sudden you got like 14 amps and you're like, oh, I gotta wait for everybody to go back to sleep again. And they may not go back asleep if your door's open. So we got to trick it, and we got to throw the latch so it thinks the door is closed, but in the meantime, the door's open so you can get to the fuse box right there. Parasitic drain on a new car is a little more challenging. However, the concept's the same. We're going to look at how many milliamps it's drawing. We want under 75. If it's an older car, it might be under 25. And if it's, let's say, if If it's supposed to be under 75, but let's say it's 80, that just means it's probably going to die like in 3 weeks rather than 3 weeks and 2 days, right? So like if you have a car that's dying overnight, you're not looking for something that's a little bit above spec. You're looking, that amperage is going to be proportional to how fast it dies. So if you have 300 milliamps, that car's probably going to be dead in like a couple days. The customer may say, yeah, Monday through Friday's great. I jump it on a Monday morning. I make it to work Monday, Tuesday, Wednesday, Thursday, Friday, but then I park it, and on the weekend I'm just done. Work is so stressful. I don't want to do anything, and I'm, just hanging out at the house in my pajamas or whatever. And then on Monday I get ready to go to work again, and it's dead, right? So like a 300 milliamps would cause it to die on the weekend, but maybe not cause it to die on a weekday because it's getting used every day and recharged every time you drive it, right? So you got to think about it like that. Whereas let's say it's a 4 amp draw, yeah, that's going to be dead like overnight easily. If not, maybe even like if you parked it at work for 8 hours and then you came out to it, it might be dead already. So your measurement should always correlate with the customer concern. Make sense? Now I'll give you another one so you know how difficult these can be. I had one, and this car was nearly bought back. This is how bad this could be. The battery would die sometimes. It might be good for a week. It would die on a Monday. It'd be good a Tuesday, Wednesday, Thursday. It'd die on the Friday. And then it'd be good for full 30 days. And then it might die 3 days in a row. And they were like, I don't know what's up with this car. Somebody put a new battery in just because. By the time I got it, I'm like, this seems like a parasitic drain. I test it, it's good. But it might not happen for weeks at a time, right? So this was a car that I would go out and I'd pop the hood and I'd just put this on periodically. And one time I finally caught it, and it was drawing like 10 amps. It was drawing all sorts of amps. And then all of a sudden it was gone. And I'm like, crap, it's gone. So when I finally caught it again, drawing a bunch of amps, I start pulling fuses. For some reason, the body control module was waking up and turning on certain random things. It would just turn stuff on, and then it'd be good for a month. And then all of a sudden it would wake up and turn stuff on. So like I ended up having to narrow it down to this body control module that was randomly waking up. So through a whole bunch of time, finally found out that was happening. A new body control module fixed it. So they could be ugly. I also had a customer wire in their Milwaukee power tool charger. They hardwired it to something. And I remember the draw was good, then it was bad, and then it was good. Then it was bad, and then it was good. Then it was bad. And as I'm looking at this scrap, now you know I don't have any hair. I'm going to tell you, fixing these problems, I'm like pulling my hair out, and I'm like, it's good, it's bad. It's good, it's bad. It's good, it's bad. And in a moment of clarity, after my stress left, in the corner of my eye, I saw a little LED. And every time it would go bad, this LED would be on, and every time it would be good, it'd be off. And I was like, wait a minute. This thing flashing is correlating with my reading. You know when you charge your power tools, how when it gets fully charged, it'll like charge and then shut off and charge and shut off? He hardwired it into the battery, and it was literally killing the battery overnight trying to charge his power tools. That's crazy. I've seen some crazy stuff. So, but this is battery related because this will kill your battery and make you think it's a bad battery when in reality it's a power tools or a broken thing or a crazy bad BCM or something. Cool, so that's the test. You can see how we're pulling fuses. And if you were to pull this green 40 amp, you'd look on the diagram, show me everything on the diagram that comes through that 40. And then we got to start to eliminate individual items that are all related to that 40 or 50 amp fuse. Make sense? So that's how you pinpoint it. And if you can pinpoint it, you can fix it. And then here's one other method that I don't personally use, but I did want to show you. So this method is not necessarily approved by all manufacturers, but it's an interesting one. So this Chesney parasitic load test, you actually set the meter to ohms, touch the meter leads together, and that's going to read some number like 0.1 or 0.2. If it's a good meter, you can delta it to 0.0, and then you're actually going to literally do almost like a resistance test of the negative ground or the chassis ground. So I'm gonna describe it. You know you got a chassis ground leaving the battery, right? You guys remember measuring ohms of a wire? It should be almost nothing, correct? Did anybody by accident measure the resistance of a circuit that was powered on? And it gave you a crazy number, a lot of times like a negative number. If you do that, if there's existing current flow, it will give you a negative ohms reading. Well, that's interesting. If there's current flow on that battery terminal and you measure it in ohms without even disconnecting it, it will give you a negative reading and you'd be like, oh, that must have current flow on it. Well, they figured out that negative reading it gives you will correlate to a certain number of amps. So they figured out this kind of trick. So this is a less common method. The other thing is that amp clamp. They'll also put the amp clamp into a picoscope and graph it so that you can see when stuff wakes up and turns off. So like if you have all your modules off and then one shuts off, another shuts off, and you can see when they're waking up and shutting off if you graph it on an oscilloscope. So that's getting a little more advanced. That's more like advanced electrical. But here's that test. I think this should work. I'll show it to you. This guy, I don't know who this is, but this is the only person I saw who actually had a demo of it. And let's see if I can, I'll skip it for you. Normally I don't like to just stick you on videos. This one I checked it out. He's doing it legit. It's just not common. He's also a crazy dude, I think. Okay, let's see if I can get sound. Ooh, sound might be an issue. A little bit. In fact, actually, I'm just going to turn his sound off. And we'll go to here. Right, so we put the meter leads together. It's about to put the meter leads together. Okay, so right there you see that 0.3. This fluke has a delta feature, so if you push the delta, it'll zero it out completely. See, watch this. It zeroed it. Ignore this oscilloscope. So now you saw that it had 0.0, right? So it's perfectly calibrated. Now you put this on the negative lead. And then you put the positive over here like on the bare metal, like maybe the alternator in this case. Okay, and then he had a connection issue, so he's wiggling it. Okay, so zero the meter out using the delta function, put it on the negative terminal of the battery, put it on the nice bare ground of, say, the alternator. Do you see that number right there? 0.000? That means it has no parasitic drain. It's actually a really cool hack because if a car comes in and you think it may have a drain, it's hard to do the parasitic drain. Hey, Bob, we've done 2 minutes.
Go on, Senor Kelly.
Living the dream. Give me 2 minutes and we're out.
That's way too long.
You know about the Chesney parasitic drain test?
I'm sorry, sir?
Have you ever heard of the Chesney parasitic drain test? Okay, check this out.
I jumped it.
Well, that would work. Okay, so if you do the negative terminal of the battery and then you go to the alternator and you put on ohms, if it reads 0.00, there's no drain. There's no parasitic drain. But you didn't have to disconnect anything. You didn't have to let modules go to sleep. You didn't have to graph it. You didn't have to wait. Make sense? So this is not generally approved by everybody, but it does seem to work. Now, if you were to get a number right here, that would be proportional to your drain. So you can actually dig up a chart and show you. So 0.00 is obviously nothing. But if you were to get a number right there, you could put that into this chart. And it would say, like, for example, 0.3 ohms, you should have 0.3 ohms if you have 35 milliamps. So that would be like normal. Makes sense? So there's this whole chart. If you really want to do it this way, you could download a chart, do the resistance, get your number, plug it into the chart, and you'll know how much you have. So if you have like 0.6 ohms, that would be, if you have anything above, like let's say 0.6, it'd be excessive. So it's a little abnormal, but it's another way that you can tell if it's got a drain or not real quick. Okay? And with that, we got some stuff to do, but you guys take a nice break, okay? Get me.